So I think it's about time to start then. Let me welcome you all here in Thessaloniki. We are very happy to have you here in this first summer school on optical interconnects. And I would like also to thank our speakers who have accepted the invitations to be here and share with us their know-how in the field. So actually, this is the first summer school that is being organized on the topic of optical interconnects. This is organized within the frame of mainly within the frame of the European project Foxtrot. So you will notice that many speakers are actually from this project, but we have also many other speakers from well-known industrial organizations and academic institutes, as you might have noticed in the program. So my name is N.Pleros, and I'm an assistant professor here in the Department of Informatics. And yeah, this is the introductory presentation today to set somehow the scene on what to expect during the following days. So let me start by saying a few words about the town that you are now. So we're in Thessaloniki. It's the second biggest town in Greece after Athens, and its name actually means the victory over the people of Thessaly. So it has been named so after the half-sister of great Alexander, which according to the myth became a mermaid after great Alexander died, and she was swimming in the sea asking the shipmen whether King Alexander is alive or not. So in Thessaloniki, the biggest university is Aristotle University of Thessaloniki, which has been named after Aristotle, the well-known philosopher, which was also the teacher of Alexander the Great. We have around 100,000 students, so this is the biggest university in Balkans. In the same area is also the Center for Research and Technology Hellas, which is among the co-organizers of this event, which is the biggest research center in northern Greece, and which actually hosts also our laboratory facilities. Here you can see a map of Thessaloniki. So this is Aristotle University downtown. So this is the campus right at the other side of the street. And CERTH is around 15 kilometers away from downtown. So some of our history in the field of interconnects as group actually here coming from Thessaloniki. So we were established, the Photonic Systems and Networks Research Group, not many years ago, actually in 2008. 1 year after we got our first big project in the field of optical interconnects, which started actually in 2010. It was the Platon project, which was aiming at producing a photonic network on chip using plasmonics as the switching technology and photonics as the hosting motherboard. In 2011, we had a second project that was coordinated by us, actually the project RAM+, dealing with optical RAM memory circuits in an integrated form on silicon chips. So this started back in 2011. In 2012, we expanded our activities in the domain by 2 new projects that we were participating. The one is Mirage, which targets an active optical cable technology with multi-core fibers, multi-level modulation formats, and 3D integrated transmitter-receiver optochips. And the biggest one is Foxtrot. It's an integrated project that started at the same time, 2012. Lasts for 4 years and deals with almost all aspects of hierarchy layers within the area of optical interconnects. So in 2013, our group was a founding member of the European cluster of optical interconnects. So a very young cluster established last year and spanning off actually of the Foxtrot project. And now we are very happy to have the first European summer school on optical interconnects here in Thessaloniki. So a few words about this ECO cluster, the European cluster on optical interconnects. This is actually an open cluster which aims to promote a strategic European roadmap in the field of optical interconnects. This is the website where you can have a look into. And there are also LinkedIn and Twitter accounts. It was founded last year in 2013, around April, if I remember correctly, and includes a large number of members, both from leading industrial partners like IBM, for example, Xirotex, and etc., and research organizations and universities. We had already two very successful events. One in 2013 in September in London. There was at the co-located with the ECO conference. There was a big workshop which attracted more than 100 attendees. And in February 2014 in Berlin, which again has had a large number of attendees. So this is the website, and everyone can become a member in this growing society actually, and getting informed about the latest evolutions in the field of optical interconnects in Europe and around the globe. So regarding now coming to the summer school organization, as I already told you, this is organized mainly within the frame of the IP project Foxtrot. Its complete title is Photonics for High Performance, Low Cost and Low Energy Data Centers, High Performance Computing Systems, targeting terabit per second optical interconnect technologies for onboard, board-to-board, and rack-to-rack data links. It includes 19 partners, actually the major European industrial and research players in the field. Here is the list of all the different organizations from Europe participating in this project. This is coordinated by Fraunhofer IZM, and this is our coordinator who will arrive in a few hours from now. Dr. Tolga Tekin from Fraunhofer in Berlin. This summer school is also sponsored and supported by different universities and research centers, like, for example, our university in Thessaloniki, CERTH, the National Technical University of Athens, so the group of photonics, which is at NTUA, and Fraunhofer IZM. By consortium clusters like the European Cluster on Optical Interconnects, and by the EPICS European Foundry, and by IEEE societies, the Greek chapter of the IEEE Communication Society and the IEEE Component Packaging and Manufacturing Society, as well as of several European projects that are active in the field of optical interconnects. The Firefly project, the Ramplas project, Mirage, and a newer one, the Rapido project. So now, a few words about the Foxtrot, who is mainly organizing also this event. So the main goal of Foxtrot is to address the field of optical interconnects in a holistic way. So around data center and high-performance computing architectures that can re-up the benefits of optical interconnect technologies. So it deals with active optical cables, including system-level lab trials, deals with optochip and top-to-board design simulators, has to fabricate all the necessary building blocks relying on many different technologies that you will have the opportunity to hear about them within the next days. It will fabricate transmitter, receiver, and router optochips, actually, so capable to be hosted on optical boards. The deployment of optical line cards and PCBs, as well as optical backplane PCBs. So this is here a schematic showing the whole hierarchy within a data center. And Foxtrot actually will take into account the entire architecture, emphasizing on the technology blocks that have to be incorporated within, let's say, a rack, and between and for connecting different racks. So here's a snapshot of the different objectives of Foxtrot. In the field of onboard interconnects, Foxtrot is targeting the deployment of an optical multimode board that will host several optochips, a transmitter receiver optochip up to 480 gigabit per second, and electro-optic router optochip with a throughput of 1.3 terabit per second. Coming to the field of board-to-board interconnects, we're going to demonstrate a backplane where the different line cards, the onboards, the boards that will be fabricated within this objective will be plugged onto this backplane. In the field of rack-to-rack interconnects, we are targeting the deployment of an active optical cable that can support advanced modulation formats. Hopefully, it can reach also data rates in excess of 1 terabit per second. And in order to enable these ambitious goals, actually Foxtrot has to work upon the deployment of a range of optochips, which includes a transmitter-receiver optochips. Here you can see the 3D integrated layout of this optochip, an electro-optic router optochip, and a complete all-optical router optochip. So now let us go into the program that we are going to have and to see how it has been structured. Today we have, after this welcome talk, the first talk coming from Bertian Offrein and Dimitris Tsiokos from IBM and CERTH respectively, which actually is going to set the scene and to state us the problems and the main building blocks that are needed in the area of optical interconnects. Then we move on, starting from the application environment with Professor Emmanuel Varvarigos from University of Patras and CTI, who is going to talk to us about data center architectures and topologies. And after a small coffee break, we are going to continue with active optical cable technologies and advanced multiplexing techniques, a talk that will be given by Dr. Paraskevas Bakopoulos from National Technical University of Athens and ICCS. And today we conclude with a talk from Fabrice Raineri from CNRS Institute in Paris about lasers, switches, and memories using 3.5 on SOI technology. Tomorrow is the date that we are going to meet actually the major industrial players in the field, as well as all of you, all the students between you at the afternoon during the postal session. So we have in the morning a session mainly driven from industrial partners, from Richard Pitwon, from Zyratex, Bertian Offrein, etc., dealing with the state-of-the-art with the commercial perspective for the optical interconnects. In the afternoon, we go to the related optochip technologies and the 3D assembly and packaging techniques until we conclude in late afternoon with the poster session starting at 5 o'clock here at the floor below the amphitheater that we currently are. On Thursday, we're going to start the session on onboard interconnects. Here we have also a speaker from the Keio University from Japan, as well as speakers from Fraunhofer IZM and IMEC. Then we move to the on-chip interconnects, starting with the chip multiprocessor configurations, a talk by me and Kostas Virsokinos, and followed by a talk from Vladimir Stojanovic, who made all the trip from University of California at Berkeley, so from the US, to speak here in the summer school. And then we start with more detailed technological building blocks with silicon photonics, plasmonics, which continues also on Friday. On Thursday, we have also our dinner, the social event in the evening at 8 o'clock. You have already received some details in the documents that have been distributed over email during the last days, and I'm also going to speak about some details in the next slides. So on Friday, we continue with the different technological building blocks. We have Laurent Vivian from University Paris Sud talking about germanium-based silicon photonics for light detection and modulation. We go on to modulators and switches with Antoine Brimon from Valencia, VCSEL transmitter technologies from Ralph Meyer, micrometer scale silicon photonics from Matteo Kerchi from VTT. Then we're going to have a lecture on how to design photonic chips, actually, from two leading industrials in the field, Phoenix and Bright Photonics. And at the end, we come to indium phosphide-based photonic integrated circuits, so two talks from Katarzyna Lawniczuk and Sonia Garcia Blanco. So since attending the course is not all that we would like you to have during these days, here in Thessaloniki. Here are some suggestions. The one, let's start from the last one, about the social dinner event, which is going to take place on Thursday at 8 o'clock in the evening at the Aioli restaurant. So I suppose you have received some instructions how to get there. It's pretty close to the City Hotel. That was the suggestion where to stay during these days. And tonight, everyone who is interested in joining could come at the Omilos Bar, which is at the coast, let's say so, here at downtown. So some of us will be there after 9 o'clock in the evening. So if anyone wants to join, he's more than welcome. Just to mention that this event is not included in the registration, so everyone then has to cover his own cost for having some drinks together. Yeah, I could not finish the talk without especially thanking our local organizing committee. I assume most of you already know Ms. Stella Marco, who has undertaken the main communication from our side, as well as Ms. Stavroula Maglavera and Ms. Theonia Alexoudi, who have been working on the organization of this event for several weeks. And I would like to conclude this talk by referring actually to an ancient Greek saying that is in front of the oldest building of our university, the building of the School of Philosophy, actually, which says, Mouses Harisithi, which means actually that before starting to learn, someone should sacrifice to Muses and Charites, or Graces. Muses were the 9 daughters of Zeus and Mnemosyne, who preside actually over the arts and sciences, and Charites were the 3 goddesses of charm, beauty, nature, and human creativity. So this saying actually means that in order to get blessed and get the gifts from these goddesses, you should first sacrifice before starting to get educated. So thank you all for your attention. I hope you will enjoy this event and your stay in Thessaloniki. Just to mention about the next event of the Foxtrot project that is going to take place at ECOC, next ECOC in September in Cannes in France. Probably many of you will be also there. So it's the 2nd annual symposium on optical interconnects in data centers. It will again host some well-known speakers from industry and academia, and is co-organized by the European cluster in optical interconnects. So thank you very much. Now it's time to call Bert, Offrein, and Dimitris Tsiokos here to talk us about the area.
So thank you, Nikos. As this is a kind of introduction, I would like to say a few things to why optical interconnects. Maybe as an introduction, by the way, to myself, my name is Bert Offrein. I'm leading the photonics group at IBM Research in Zurich. And we work on silicon photonics, optical packaging, as well as also quantum photonics. So why optical interconnects? Why optics? It's clear we know optics from telecommunications, long-distance communication, and I will come to that in the next slide as well. In computing, there's not a lot of optics yet, but it's coming. And why is it coming? What are the reasons? Well, it's to a large extent because of the physics of electrical links. When we scale systems and we have to scale the performance, so the bandwidth of the communication, we start to run in larger and larger issues because of increased loss. When you increase the data rate in a digital electrical link, when you increase the frequency, the losses increase, you get a higher crosstalk, and you get also problems with resonant effects. Just to indicate this, here we have, for example, a computing system with two boards interconnected through a backplane. And just look how the electrical signal is going from one CPU to another CPU. The signal is generated here, is going through all kinds of interfaces, through a carrier substrate. The processor is never mounted directly on the board, but it's mounted on a carrier substrate, which acts as a kind of fan-out. And then you go through the card, and then the backplane. So you have all kinds of interfaces where you have reflections, where you have disturbances. And if you go to higher frequencies, you get problems, for example, with resonance effects that appear here in the printed circuit board, where you have a via and a line, and you have these stubs where resonant effects occur. And they all deteriorate your systems and in an electrical link, and that really limits the capability to increase the bandwidth and to increase the number of channels. Because what can you do if you want to increase the bandwidth? You can increase the data rate per line, and you can increase the number of lines. But if you increase the number of lines, you get closer together, so you have more crosstalk. And if you increase the data rate itself, you get higher losses. So it's some fundamental challenges, and I try to list that here also in some numbers. But what's important to realize is that, say, the big difference in the physics between optical links and electrical communication is that in electrical communication, your signal is your carrier. So you have an electrical line and you charge and discharge that line, and the signal is directly the carrier, which means that if you change the frequency, you also have to change the line itself in order to be able to have the impedance you want. Whereas in optics, the physics is determined by the nature of the light. It's really optical propagation, and the data is modulated onto the optical signal. And this also causes that, say, the bandwidth that you have available in optics is just tremendous, just between, say, the two of the main bands for optical communication in the telecom domain, 1300 and 1600 nanometer, we have 50 terahertz bandwidth available. And this is, of course, completely different in the electrical domain, where you have, say, the bandwidth just directly of the carrier, which is, say, up to 10, 25 gigahertz, which is available. But then you also have to take into account the length. It's not just the bandwidth, but it's also the length over which you propagate. And this is where optics has a tremendous advantage compared to electrical communication. In the bandwidth length product, say, of an electrical coax cable here, about 100 megahertz kilometer. If you go to a multi-mode fiber, it's already clearly larger. So what I take into account here is that you have a signal which is propagating, and then over a certain distance you get issues because, for example, when you have a single bit that's propagating, the bit gets smeared out because of various effects. In the multi-mode fiber, the main effect that's occurring is just modal dispersion. So this makes that your bit, which enters into the fiber as a nice bit, starts to overlap with the adjacent bits. And when that happens, you have reached the maximum distance. And of course, this is an issue also of the bit rate that you have. So that's why it's the multiplication bandwidth times length. If you go to a single mode fiber, you only have one single mode, so you're not limited by modal dispersion, but you're really limited by the chromatic dispersion. And I wrote here a number like larger than 5,000 megahertz kilometer, which is, to say, taking into account the chromatic dispersion at 1550 nanometer. In addition, of course, you also have to say, compare the larger bandwidth again. This is for one single signal, but in addition, you can have wavelength division multiplexing and, say, various colors that you transmit through the fiber. Today, what you see, where there's a kind of boundary, that is that for all links that have a larger bandwidth length product than larger than 100 gigabit per second times meter, You normally see that it's optical. If it's shorter, in most cases it's electrical. A very important aspect, of course, is also the propagation losses. In an electrical coax cable, 1 dB per meter. If you compare this with a fiber, multimode fiber, about 3 dB per kilometer, and a single mode fiber, 0.3 dB per kilometer, you see that there is a tremendous difference here, say 3 orders of magnitude. And this whole combination, of course, makes that from a power efficiency point of view, there is a fundamental advantage of going to optics compared to electrical communication. You also see, of course, here directly the reason why optical communication first comes in when you have to travel over long distances. Because electrically you would have to say, have too many repeaters in order to be able to bridge the overall distance. For computing, a very important aspect is the larger density of optical links. When you just compare the amount of data you can transmit through one single fiber compared to what you can transmit through one electrical cable, as discussed here, it's clear that optics has a much higher density. Here I list, say, the various distances over which optics came into play, say the ultra long distances. Since the 80s, we see, based on the, say, invention of the fiber as well as the erbium doped fiber amplifier, optical communication going into local area networks, and where we are currently, say, working on, and also all the projects that Nikos mentioned are working on, is really in this area. And today we see that for, say, rack-to-rack and card-to-card communication, optics really starts to be established. And on-card and on-chip, towards the chip, that is something that is currently under research and development. So yeah, I talked about the density advantage of the optics. Here you see just some pictures to give you a feeling about this. Just compare an electrical cable with an optical cable. And then, based on the first slide I showed you, imagine the difference in bandwidth capability of the fiber compared to the cable. You also see already here that the optics gives a much linear solution if you want to interconnect, say, rack to rack with fiber cables compared to electrical cables. Here, in this case, the whole rack becomes so heavy by mounting all the electrical cables that if you wouldn't bolt it down to the floor, the whole rack would just fall backwards. Whereas with optics, you don't have that issue. And density is very important because what you saw in the first slide where I showed you these two boards connected through a backplane, we want to have massive communication between the processors from the board to the backplane, back to the other board. So density of connectors is a very important aspect. And here you see, for example, an electrical board backplane connector. It's mounted on a board here on this side, and then you can connect it to the other board, which is mounted like this. And you see here in similar areas in optics, just taking standard technology available today, we have more or less a factor of 10 more, where you have to take into account that here, look at the area of where the fibers are. There's a lot of free space available, and still the fibers here are at a pitch of 250 micrometer. You can make that much closer together. Electrically, this is really much harder to do. And the same holds for the board level, and that will also be discussed in more detail in the workshop. Communication is becoming the bottleneck and is becoming more and more important. And you see here, say, in terms of the scaling of processor chips and scaling of the number of pins that go out of a processor package, say from several hundred to several thousand, that the communication aspect of building a computing system is becoming more and more important, and is becoming more and more a challenge. and it's something that needs to be worked on. Because if you scale a system, and you see here with what kind of data rate, or sorry, with what kind of rate the performance of, in this case, supercomputing systems is scaling, it's a factor of 10, just taking into account the trends as we know them from the past, and you can extrapolate them to the future. We know that's a factor of 10 every 4 years, so more or less 3 orders of magnitude every 10 years. And that means that you have to scale all aspects of the system by 3 orders of magnitude every 10 years. So not only the processor performance, not only the memory, but also the interconnects. And that's really something that holds at all levels of the system. As you see in this slide, as an example on the IBM Blue Gene, you have, say, the communication between racks, but you have also the communication within a rack. And then within a rack you have multiple boards, so you have the communication within one board, within one card, and within the processor. And at all levels you have to increase with 3 orders of magnitude, which means that new technology is required also for all these various levels of the system. And what does that mean? How does an optical link look in the end? Electrically, it's pretty simple. You have an electrical signal and you receive an electrical signal, and in between you have a copper wire. Optically, you need many more components. In order for optics to make sense, you have to make sure that the data rate is high enough, so you have to serialize several data streams into a high-speed data stream. Then normally you cannot directly insert the signal that's coming out of the processor into the laser. In this case, this is a link for a directly modulated laser. You need some circuitry in between, preamplifier, laser driver, such that the signal that is coming from the processor is converted into an electrical signal that is able to switch the laser on and off, or not, say, going from the 0 to 1 state, low power to high power, in the right way. Then you couple the light into a fiber, and you detect at the photodetector, generating a current. You have to transfer this current into a voltage through a transimpedance amplifier, maybe some additional amplification, and then you have to deserialize. So you see that in order for an optical link to make that happen, there is all kind of steps in between that have to take place, and there's a lot of additional components that have to be put in place in order to make this optical link work. So let's look at this again. Where to position all these various components? So again, a board, the backplane, processor, memory. Here the signal is generated, and you go to another board that's maybe mounted in this same backplane over here, or you go to another rack with, say, similar geometry, where to mount all these individual components as you see them here. Well, today what you see is that the optics is mounted here at the edge. Let's jump back to this picture, which means that this electrical link, as you see it here, is covering this whole distance. Right? And then you have a driver chip and the laser and so on. This means that although you have some advantage of the photonics, because you bridge quite a distance, which you probably are not able to do with an electrical cable, you still have the electrical signaling here, which can cause problems if you go to higher data rates, because you still have the signal loss. You need to re-amplify the signal. So from an efficiency and also density point of view, this is not ideal. You would like to make this electrical link shorter. So you can mount the optics also on the board itself. or maybe even better, onto the processor, such that you have really a very short electrical link. Because that's where electrical links are really good at, in short links. Or maybe in the end, even with the processor itself. Now, what we see happening is that over time, the point where you do this conversion is moving closer and closer to the point where you generate a signal, such that the electrical link itself becomes shorter and shorter. But you cannot make this change in one step. You have to do it little by little, because we have to learn the optical technology, and we have to be able to establish the optical assembly technology that enables, say, a massive optical signaling away from the processor right here. So we saw a lot of, say, advantages of photonics and capabilities. Why is it not yet fully applied? What are the challenges? Well, I indicated already we have a large number of components that need to be integrated. So this means additional assembly effort, means additional cost. So cost is always driving, and there's nothing simpler based on integrated technology as we have it to make an electrical connection. So you will only apply optics if electrical technology is not able to do it anymore. So only there where electrical is not able to cover, optics comes in, but that means that we need an ultra high-end solution, ultra high bandwidth. So, and for this, the technology has to be established. Then there have been, and there still are, reliability concerns. What happens if the laser dies, for example? And also a very important aspect, computer system designers, they know electronics. So that's what they like to add. They first need to be convinced that optics is a really capable solution. And in the end, it's all about the cost. Technology always finds the way of the lowest cost. So related to this large assembly effort and the increased number of components, optics has a fundamental issue that needs to be tackled in order to have massive integration into a computing system. Okay, that's what I want to say. Maybe you have any questions. Thank you. Okay.
Okay, my name is Tsiokos, and I'm from CERTH here in Thessaloniki. I will continue the introductory talk, but before I do that, I'd like from my side also to welcome you all in Thessaloniki and in the summer school. I would also like to thank all the speakers that kindly accepted our invitation and they came in the summer school, and also the organization committee and all the members of the FOSNET lab that have done a great job in organizing this event. My talk will be on optical interconnects, and it will be basically an overview. I will give you the highlights on the application and the key technologies that are involved in the complete path of optical interconnects, and how these steps will be reflected in the lectures that you're going to hear during the summer school. For my first slide, I chose to show you this schematic from Luxtera, which says fiber to the chip. I put it there because I think it's a very appropriate schematic to show it actually represents the trend in optical interconnects, which is to push light further deeper and deeper into computing machines, and eventually use it to transfer data on the chip. So as an introductory slide, I just want to give you an illustration of the major technologies that are involved in the optical interconnects ecosystem, and what we are going to listen during the summer school. And that will start from on-board interconnection. You're going to hear about all the optical components that are required at every stage, how 3D integration can be used to develop systems on-chip. You'll also listen about optical PCBs and how that can be the new motherboard. We'll hear about board-to-board interconnection, rack-to-rack interconnection systems and architectures, of course, assembly and packaging for photonic chips, and finally, photonic integrated circuit technologies and design tools. There's also a camel over there, which apparently has a share in optical interconnects evolution. We'll see right next to why is that. So I'm using this basic schematic to develop my case. And let's say this is a typical electronic PCB with some chips on it. Let's just ignore the mind in the middle for now and see how this develops in simple terms. So we're going to have some data in one chip, and this chunk of data will have to be moved, transferred to a different chip on the same board or somewhere else outside the board. I'm using the phrase big data because apparently it's very trendy, but for a reason, and that is because there's a lot of stored data up on the internet, on the cloud, and experts say that by next year, the total stored digital data will be of the order of a few zettabytes, and that's a big number. So I guess that's why they call it big data. So eventually, there are going to be a lot of chunks of data in each chip that will have to be transferred to another chip. By using state-of-the-art electrical interconnects will be something like trying to do this, or even better, trying to do this. So here is where the camel comes in. So by using electrical interconnects, it will be like trying to squeeze a camel through a needle head, which apparently is not possible because we're going to have to transfer high-frequency data over electrical links, which, as Bert mentioned, is quite difficult, if not impossible. So let's do it differently then. Let's do it optically. So let's say this is a basic optical connection between the two chips. So what are the basic components and technological devices that will be necessary to do that? So first of all, the optical source. It's a very basic component, and I've added a vertical cavity surface emitting laser here as a VCSEL as the optical source. And VCSEL seems to be the right candidate to do that in optical interconnects for many reasons. First of all, they can be directly modulated, and there has been experiments showing modulation up to 40 or 50 gigabit per second. They can also be developed to operate in all different frequency bands, optical bands from 850 to 1300 to 1550 nanometers, depending on the application that you want to apply them. They can also be developed for operation in single or multi-mode, and most importantly, they can operate with low power. They have very low threshold currents, and they can be developed on a low cost. There's also been arrays or matrices of VCSELs developed, and that is another reason why the cost can be significantly reduced, and then use the VCSEL arrays as multi-wavelength sources. Another way to do it is have an external modulation scheme. So you use another a continuous wave laser and externally modulate by using a modulator. So that's another component that has a role in might have a role in optical interconnects. And of course, you can also use the modulator as switches, as we will see later on. So what about the other side, the receiver side? So the major component required there is the photodetector. And as we will see later on in the summer school, silicon germanium technology is there to realize that. Apart from any electronic amplification stages, there will be a need more or less for optical amplification at some points of the link. And we'll see in the summer school how this can be done by using semiconductor optical amplifiers or even erbium-based components, integrated components. So at the end, the chip might look something like this. So on one side, there will be the typical chip, like a processing chip or a memory chip in electronics. And on the other side of the chip, there's going to be the optoelectronic interface. So it's going to be the point where the data will be generated in the optical domain and will be transmitted in the link. So by using either a VCSEL or an external modulator and perhaps a multiplexer to multiplex multiple wavelengths on a single output link. And of course, on the other side is going to be the components for the receiver, the multiplexers and the photodetectors. These are the relevant talks throughout the summer school that will talk about useful components and what has to be developed or is being developed. It's going to be a talk later on by Fabrice Raineri from CNRS in France, talking about laser and switches and memories. On Thursday, there's going to be a talk by Thorsten Wolbrink from AMO, talking on nanometer scale silicon photonics building blocks. And then the rest of them will be on Friday. There will be one talk by Laura and Viviane from the University of Paris Sud, talking on germanium-based light detection and modulation. Antoine Brimont from UPVLC, talking on silicon modulators and switches. Ralph Meyer from Technical University of Munich, talking about VCSEL transmitters. Matteo Kerki from VTT on micrometer scale photonic components. Katarzyna Lavniczuk from JEPIX and the Technical University of Eindhoven, talking on indium phosphide-based integrated components. And last but not least, Sonia Garcia Blanco from the University of Twente, talking on integrated optical amplifier technologies. So I'm coming back to my board. You're going to see it quite a lot, this board. So we saw how what do we need for a simple connection from one chip to the other. But this is not a realistic scenario. You will need the mind. So here is where the mind comes in to decide whether the data has to be transferred in a chip on the same board or leave this board and go to another board or to another machine. And this will be a router or a network on chip, as they call it. This is a very popular schematic. Probably you've seen it in other presentations as well. So the idea here is that you're going to need a router to seamlessly route the signal either to a different board or a different machine. So you have a board-to-board or rack-to-rack interconnection system. Or it will decide if it is an on-board, if it's destined to go to a different chip on the same board, it will do just that seamlessly. Now, necessary components for on-chip interconnects are also optical switches, and these can be either ring resonators or Mach-Zehnder interferometers, and of course, multiplexers and demultiplexers will be required to deploy WDM technology and exploit the optical bandwidth. Now, related talks are from Kobi Hasaroni from Compass EOS. He will be talking on Wednesday on router optochips and interfaces. A talk by Vladimir Stojanovic from the University of California in Berkeley, talking about photonic networks on chips on Thursday. And on the same day, N.Pleros and Kostas Visokinos from the Aristotle University of Thessaloniki will talk on optical interconnects for chip multiprocessors. So another issue that comes in is how do we do it? How do we develop a network on chip? And that is by deploying 3D integration. 3D integration, this guy is wearing glasses. I hope that people doing 3D integration will not have to wear them. But 3D integration is very challenging, and they've already started using it in the electronics industry. So what needs to be done now is to squeeze in photonics, a photonic layer in that 3D integration process. typically, and in general terms, 3D integration, what it's trying to do is to change the way things are integrated now. So typically, you have a board where you integrate a lot of different chips and different functionalities in a horizontal plane, like a board. But 3D integration will take all the functionalities and all the different chips and put them on a single vertical stack to minimize the dimensions, increase the functionality, and decrease the energy requirements. So this is a nice schematic, and this is how they envision it at the group in the US at the University of Colorado. So I think it's a pretty nice schematic to show how 3D integration can be achieved in the future. There are all of different layers. One could be RAM, memory, FPGAs for processing in the electronic domain, cache memories, and somewhere in there will be an optical network, a reconfigurable network router. Now, all these different layers will have to communicate somehow, and this is going to be achieved by using through silicon vias, or TSVs. Now, this is another schematic, another attempt on how to do it in simpler terms, and how Mirage project and Foxtrot project is approaching this. So it's a side view of how this 3D integration might be implemented. So we have a photonic layer in the middle where light can travel, like a photonic waveguide, a silicon, an SOI wafer, and it shows how optical sources and optical detectors can be bonded, can be flip chip bonded and assembled on top, where light can be coupled in and out of the photonic layer, while at the same time, by using an interposer layer, active electronic circuits like amplifiers and drivers can be assembled on the bottom side of the same chip. So eventually, the optical active components and the electrical circuits will be communicating electrically via vertically positioned TSVs. At the same time, the optical signal can travel uninterrupted in between. And a critical component here is the out-of-plane grating coupler, which is basically a component that can be directly written on the photonic layer and will couple light out of the photonic plane, in and out to the photodetector or from the optical source. Relevant talks is one on Wednesday by Jochen Kraft from AMS. He will be talking about optochips and 3D system in package integration. And again, quite relevant is a talk from Vladimir Stojanovic on Thursday. So what about memories? I mentioned about or probably I didn't, but there's supposed to be a memory electronic circuit that our network on chip will have to work together and interplay. But what if we try to do that optically? Well, it sounds distant, to be honest, and it sounds very challenging as well. But if you see from the statistics point of view, you may say it's also necessary to some extent. So what we see here is that the speed of the electronic processors, CPUs, is increasing 3 times faster than the electronic memory circuits. So that essentially generates a gap in the two performances. And this is also called the memory wall problem. So one way to go around this is to forget the electronic memory, either it is on chip or outside the chip, and instead develop an optical memory system on chip that will be able to communicate with the rest of the chip by using WDM technology. This sounds a little bit vague, a little bit general, a little bit distant, as I said, but the truth is that there have been some first steps towards this vision. Specifically, a a single optical flip-flop, which is the basic memory unit, it was experimentally demonstrated in our lab here in Thessaloniki by using two coupled Mach-Zehnder interferometers integrated on a single chip. And its features and its specifications have been then used to design the overall optical RAM. So there have been architectures proposed, and there have been simulations showing that this might be a realistic scenario to overcome the memory wall problem. Now, relevant talks on optical memories. Fabrice Raineri, I think he will be mentioning some memories, architectures, and possible applications. And talk by N.Pleros and Kostas Visokinos will also include a part on that. They will be talking on optical interconnects for chip multiprocessors. So I'm coming to my board again. And we've seen, to summarize a little bit, we've seen the necessary interfaces, optoelectronic interface between a chip and another chip on the same board, and what are the basic components that are required for this. We've seen also what is the need for routing chips and processing chips and photonic networks on chip. So the question here is, how do we interconnect of these? And the answer, of course, is a photonic interconnecting platform. In other words, it is the optical PCB. So electrical PCBs have to be replaced by optical PCBs. And this is another schematic showing how this might work. So we have a whole chip system assembled on top of our optical PCB, where light can be transmitted and coupled vertically into the PCB waveguide, and the other way around, coming into the receiver. There has been quite a lot of work, and currently the work's developing in projects like Foxtrot and Firefly on multi-mode and single-mode glass and polymer waveguide PCBs. And I've also included a nice picture which basically shows how that light can be actually wave-guided in an optical PCB. So that is a reality. So we've seen what are the requirements for on-board interconnects. Now we go a step further. What if light has to be transferred from one chip to from one board to a different board, right? So that can happen by hooking up all these different boards to a single optical backplane. And then again, light will be routed via vertical coupling structures from board to board. So we've got quite a lot of talks on optical PCBs throughout the summer school. We've got two talks from Richard Pitwan from Zyratex, or better say Seagate. I recently noticed that. On optical circuit board design and optical interconnects in data storage systems on Wednesday. Another talk on Wednesday by Bert Jan Offrein from IBM on optical interconnects for energy efficient data centers. Energy efficiency and low cost are the main drivers, as Bert said. So this is a very important issue. Then Marika Imonen from TTM on Wednesday will talk to us about optical PCBs and how the optical motherboard eventually might look like. Takaki Ishigure from Keio University in Japan will talk to us about the design and fabrication of multimode polymer waveguides for PCBs. And Dionysis Manis and Lars Brusberg from Fraunhofer IZM will talk on Thursday on single-mode glass-based PCBs. So we've seen the board-to-board interconnection scheme. Now the next step, of course, is to interconnect different machines or different racks. Either it is right next to each other or a few hundreds of meters down the data center room. So we do that by using active optical cables. Apparently they call it active because all the optoelectronic components for transmission and reception are assembled into the package of the connector. Now commercially available components 10 gigabit per second. There are efforts towards 25 or maybe 100 gigabit per second. But what about a big number, like 1 terabit per second? This is a big number, but I guess it has to be big in order to address the big data problem that I mentioned earlier. So this is an effort that is currently being done in a European project Mirage, which aims at delivering that sort of number by combining different technologies like WDM technology. They'll be using more than one wavelength to transfer data through the cable. PAM4 modulation formats to double the capacity of the link, and spatial multiplexing by using multi-core fibers as the active optical cable basic link. So later on today, Paraskevas Bakopoulos from National Technical University of Athens will give us more details on his talk on active optical cables and advanced multiplexing techniques. On Wednesday, Jérôme Touy from TE Connectivity will give us the industrial perspective of active optical cable technologies. There's also one talk scheduled for Wednesday by Mellanox, but I'm not sure if eventually someone will make it. They had to have some last-minute changes due to personal reasons. So even if we say that we have all the technologies that we need and the components and the systems, we still have to work out the network architecture, because data centers eventually are very, very complex. So what we need is to have the necessary topologies in architecture in order to reduce the cost, increase the throughput, and reduce the resources that are required. So in that respect, Manos Varvarigos from the University of Patras, later on today, I think it's the next talk, will talk to us about the data center architecture and topologies. And Professor Koziris from the GRNet, which is the Greek research network, will talk to us about the Okeanos cloud computing platform and what are the needs for such platforms from Optical Interconnects. So one important question here is how we develop all these components and all these devices. What technology do we use? I've used this table here because it summarized two mainstream technologies. One is indium phosphide, and the other is silicon photonics. Sometimes people talk about these technologies like they're competing, but if you look closer, you'll realize that they're actually complementary. And that is because there are a lot of components that can be developed by using indium phosphide technology, but the main drawback is that you cannot actually integrate that with currently available technology for electronics that electronics use. On the other side, silicon photonics have that. They seem the ideal candidate to do that, to be integrated with the electronics. They're CMOS compatible. But there's one major problem. We don't have a silicon laser yet. So the truth might be somewhere in the middle. So these two technologies have to be combined and be brought together on a common platform. So the issue there would be how to use them to have effective systems and effective optical chips for optical interconnects on a low cost, and eventually be competitive to electronic counterparts. We also have a lot of talks relevant to integration technologies and materials. Against Fabrice Raineri, that will be talking about 3.5, and Katarzyna Lavniczuk, that she will be talking about indium phosphide platform and JEPIX. Thorsten Wolbrink from AMO, his talk will be based on nanometer scale silicon photonics. Likewise for Antoine Brimond, and Matteo Kerki will talk to us about micrometer scale silicon photonics, and Laurent Vivienne on germanium-based photonics. Now, apart from the mainstream technologies, there's also an underdog technology like plasmonics. Plasmonics is a science that has been researched for decades, but it's only recently that people decided to look closer and use it for datacom applications. And the reason for that is because people are trying to reduce the size of optochips, and plasmonics seem to be a very good candidate to address that target, simply because by using plasmonics we can confine light in very small dimensions, something that optics cannot do because they're diffraction limited. So let's see how Platon did it. It's a research project that N.Pleros mentioned earlier, and it was the first attempt to use plasmonics and combine them with silicon photonics to deliver components and systems for targeted for optical interconnect applications. So they developed this, they used dielectric load surface plasmon polaritons by developing this structure. So they actually achieved to transmit data guided at the dielectric gold interface right here, where the light is really, really confined in small dimensions. So you can achieve small footprint, and they've demonstrated transmission at 40 gigabit per second. Now, plasmonics seem to be really appropriate for interfacing photonics and electronics, and that is because they use the metal, right? They can also develop thermo-optic induced switches for the same reason, on a very low switching power requirements. However, the propagation losses seems to be the catch so far in plasmonics. Professor Dero from the University of Burgundy in France will give us the details on plasmonic integration technology and building blocks on Thursday. An equally important issue here is the assembly and packaging. And the reason I'm saying that is because people know that a big part of the cost in photonic circuits and photonic components lies on the packaging part. So assembly and packaging essentially means putting a lot of different functionalities in different chips, different technologies, putting them together on a common platform, a common substrate, or a common board, and eventually deliver fully packaged optochips or systems. And assembly and packaging in optochips has to have features like high density, has to be cost effective, low power, have a thermal management, a good thermal management, and mechanical stability. Features that have to be combined in order to be competitive against the electronic industry. Now, Tolga Tekin from Fraunhofer IZDM will talk about packaging and assembly for 3D optochips on Wednesday. And on Thursday, Gert van Steberke from IMEC will continue by talking about optoelectronic assembly and packaging and on their work at IMEC. Now, before I conclude my talk, there's another highlight that for sure has to be mentioned, and that is the photonic integrated design tools. And the thing is that we've got all the components, we've got all different technologies available at the moment, and optical design is a reality. And optical chips eventually would be very complex to do. So we need photonic design tools like they did in electronics to achieve efficient design and efficient fabrication. Now, the process here would be that the designer will need to have a tool from which he will be able to extract built-in components, irrespective of the foundry, put them together and develop the circuit, the circuit that each user would want. They would be able to do circuit simulation or even numerical simulation, and as soon as this is finalized and optimized, you will also need to generate your mask that eventually will be submitted to the foundry, to the targeted foundry, to develop the chip. Arjen Bakker from Phoenix Software and Ronald Brocke from Bright Photonics will give us the details on on how to design photonic chips and the available tools on Friday. So to summarize, I've I've added the circle of life of optical interconnects that more or less describes what you will also hear throughout the summer school. And starting from the developing technology and the fabrication technologies, either the silicon photonics or 3-5 photonics or plasmonicos or any other, we'll see how we can use them to develop all the active and passive necessary components throughout all the stages of the optical interconnects, and how we can use them to design and build optochips by using 3D integration and photonic integrated circuit design toolkits. You will also hear about assembly and packaging, which is equally important, and optical PCBs, which is the way to put everything together. And you also hear throughout different talks on on-board, interboard, and rack-to-rack interconnections by using active optical cables, and of course, architectures. So this is the end of my talk, but the beginning of the summer school, so I hope you enjoy the rest of the summer school. I guess you will have the chance to pose your questions to all the speakers later on in the summer school. So if you don't have any questions, I'd like to call, to start the application sessions and call Professor Varvarigos from the University of Patra. He will be talking about data center architecture and topologies.
So, my name is Manos Varvarigos from the University of Patras, and my talk is going to be on data center architectures and topologies. An overview of the talk is the following. Since it is one of the first talks, I will do some introduction, or present some introductory slides on the data centers and also on supercomputers, because data center and the supercomputer technologies are very much interrelated. Then I'm going to talk about possibilities for the topology, for the topologies that you can use in data centers and the supercomputers, the network design. What are the performance metrics that are important in judging the different topologies and the different designs. I'm also going to present some results on the traffic profiles. So, what type of traffic do we expect to have in a data center or in a supercomputer? In some cases, the traffic has some symmetry properties and some structure. And then I'm going to talk about optical interconnects and then focus on the onboard design level, what Dimitris called the optical printed circuit board, and look at the topology layout at that level. I will present the methodology for designing such layouts for the board, and also we are developing some tools, some tool for designing such interconnects and some preliminary results also. So there is a large number of, data centers are becoming economically important, very important economically, basically because of the large-scale applications that are being developed. So webmail, web search, YouTube, Facebook, all of these applications require a lot of storage and a lot of processing that has to be done somewhere. This is done has to be done therefore at the data centers. And especially the Facebook paradigm changes vastly the type of data that's being created, because in the past we had some data being created mainly by content publishers, but now everybody creates some content, and there's a huge number of people, so this is going to increase a lot the storage requirements, and also the fact that probably data has to be stored at different places across the network, close to the user. So these applications are driving the need for data centers, as well as the cloud computing paradigm, which is also becoming economically important, in the sense that people now do not rely only on the resources that they have available on their laptop, but they can also lease resources from data centers and in a flexible way, in an on-demand way. And there are many companies that rely for their IT infrastructure, they rely actually on cloud computing. So these two factors together increase the importance of data centers. And as we know, data centers are therefore essentially warehouses filled with computers, and and also communication devices, where usually the computers in the data centers are commodity hardware. So they are not, there are many cheap computers. And we have data centers that have of the order of 500,000 servers or even more. And one of the issues there is that that these data centers have to be deployed in a modular way and in an easy way. Therefore, usually, this is done in a hierarchical way. We have a lot of servers that are packed in a rack. Then many racks are put in a container, like the shipping containers. I don't know if... And then these containers are put in warehouses in order to reach big numbers. And each of these containers, which is called a pod, contains of the order of 2,000 servers. And so this is for data centers. On the other hand, we have also the supercomputers, which are... the difference is that here the computations that take place are special purpose computations, like for physics, for weather forecasting, for scientific applications, for financial or military applications, etc. So here, usually we rely on high-end systems. So we want here the computations to take place very fast. We want a very good speed here. Therefore, the model here is usually the dedicated execution model and not the virtualized services model that we have in the cloud. However, the architectures that are used both for supercomputers and for data centers are often very similar, but there are also differences. So, for supercomputers, there is also a list of which are the most, the biggest one, the fastest ones. There is a document where everybody wants to be that contains the 500 most powerful systems on the planet. The most powerful, as of a few months ago, was this Tiani computer, which has a total processing power of 35,000 teraflops at the cost of 400 million. It also has, of course, some important energy cost. So we see that these supercomputers are also very economically important. They have a lot of cores also, 3 million cores in this system, which have to be interconnected. So the important thing for us, for our team, is how really to design the topology for such systems, because all of this that is going to interconnect these millions probably of processors. So in terms of topologies, there is a large number of topologies that have been proposed. The literature is very rich, probably of the order of 1,000 different topologies exist, and with different characteristics, and of course everybody who proposes some topology proves that his is the best. So for different, under different criteria, some of these topologies are better than others. One could, in general, categorize the different topologies in two general categories: the indirect topologies and the direct topologies. So in the indirect topologies, the situation is that you have, for example, the processor, and you have the memory, so there are the processors there. So you have some entities that communicate with some other entities, which are at the edge, and you have the communication devices in between. So, for example, in this case, this is a butterfly network, and then you route your data through this butterfly, or it may be a tree topology where data goes like that, up and down, or it may be a fat tree topology, because this will suffer. I mean, this has a lot of data will have to pass through this route if you have a tree topology. A solution that they have is that they use a fat tree topology where these links are really very wide, so you have multiple links there, or equivalently, you have multiple nodes here, so that you have many ways to go through the route. So these are indirect topologies in the sense that there is a communication network in between that connects these different servers. And the other alternative is to have direct topologies, for example, two-dimensional grids or tori, or hypercubes, or many other topologies, where the idea is that each of these nodes really is not only a communication node, but it also contains some processing elements and some memory elements. So each of these guys is a router, and also has some processors and some memory, and all of these nodes, so the different paths have to be found between different nodes for the corresponding processors or other entities to communicate. And so different topologies have been proposed. They have different performance metrics. For example, they have different diameters, different bisection widths, etc. Now, in general, the topology affects greatly the system performance. For example, it affects the capability, the delay, because the delay will in some way depend on the diameter, what is the length of the paths on the topology. And it may depend strongly on the diameter, as in the case where you may have stored forward switching, or it may depend in a weaker way on the topology, as is the case when you have a cut-through switching through these nodes. By cut-through, I mean that when the packets arrive at some node, you do not have to wait for the whole packet to arrive. You can start forwarding the first bits of the packets while the last bits have not yet arrived. So you go fast through the nodes. But again, the delay is going to depend on the diameter. Okay, even though the constant in the delay that multiplies the diameter is going to be smaller. So you have different topologies, and what you have is that you start with some nodes. For example, this is some supercomputer by Cray, which uses a three-dimensional torus topology. Three-dimensional torus means that there are 3 dimensions, and each node is connected with 2 neighbors in each dimension. Therefore, you have a total of 6 connections to other neighboring nodes. And each node here has some CPUs, it has some memory, etc. So you start with a node, and then you put the nodes on a blade. You may have some topology on the blade here, so you may have a two-dimensional mesh, a 2x2 mesh here. And then the blades are put on a rack, and you may get a 4x16 Tor topology in this case. And of course, there are communication links going to other racks. And if you put all the racks together, then the system is a three-dimensional torus with dimensions 25 by 32 times 16. Okay, so the issue here is, okay, this is one way, one topology, the torus topology is popular with electronic interconnects, but I want to see what will be the good topologies to use when we go to optical interconnects. Is it going to be the same topology, similar, or very different, probably? So let me here describe one of the topologies that is very popular, especially in data centers. This is the FAT3 topology. It started actually from high-performance computing. The connection machine 5 in 95 used this topology, where you have here you have the processors, you have a tree, but because a lot of traffic has to go through the route, you have it's a fat tree. So as you go up the route, these links become wider because they have to carry more traffic. So in the probably this half of the nodes may have to send something to the other half, in which case a lot of traffic is going to pass through this. That's why they have to be wide. This is the Lyserson topology. And then this was extended in modern data centers. In this case, where instead of having a single node here, you have multiple nodes which share this bandwidth among each other. Therefore, you may have a situation where you have these racks here, and you may have different layers. You may have, usually it's 3 layers, but it may be more, and where you have the communication nodes at each layer being fully connected to communication nodes in this layer, which are fully connected to communication nodes here, and then you go down on the other side. So this is a popular topology, but it's also very expensive, because if you count the number of switches that you need, if you count the number of cables that you need, it's going to be it's pretty large. And it does not scale to very big systems. I mean, it scales, but it's going to be expensive if you go to tens of thousands of processors, of servers, etc. And of course, people try to reduce the cost. For example, you could have less switches here, but then this reduces the performance in the sense of the bisection width, which is an important parameter of interest. Because when you have uniform traffic, it is quite possible. By uniform traffic, I mean that there is no locality in the communication. It is quite possible that a lot of traffic will pass through this upper layer, and if you have a reduced number of switches here, you are going to suffer. So in terms of, let's look at what are the performance criteria of interest when we design a topology. Probably the most important one is the bisection width. By bisection width, I mean if you have some network and you divide it into 2 equal halves, and in this case I have a linear array actually, and here I have a 2-dimensional grid or 2-dimensional mesh, and if I cut it in 2 halves, what is the bandwidth that connects the 2 halves? Okay, so here I have a bisection width of 1, while here I have a bisection width of square root of n. This is a much better topology than this topology in terms of the bisection width, and one can see it by looking at what traffic this link will have to carry. Okay, so if you have n over 2 and another n over 2 nodes here, you are going to have n square over 4 traffic here, while here this is going to be proportional to square root of n. So here this is going to be it's a much richer topology, and this is evident, this is proved actually by the bisection width of the topology. So when we design a topology, we want to have it a big bisection width. We want to have also a small diameter. So if it is the diameter here will be of the order of n, here of the order of square root of n, if we have a similar number of nodes in the two topologies. So this is also better than this in terms of the diameter. Path diversity helps with fault tolerance, etc. So you want to have many paths between every pair of nodes. And also, so these are independent of, this is for uniform, independent of the traffic patterns. These are parameters independent of the traffic pattern, but also because the traffic pattern is usually not uniform, but it has some locality, you are interested in other things, like what is the ideal throughput for this non-uniform traffic pattern, and also what is the average distance, because you may have a large diameter, but if you have some locality in the communication, the average distance traveled may be much less than this. Okay? So these are the important parameters when you design the topology. And now the next thing to look at is what is the traffic that is being generated. And especially for high-performance computing applications, the traffic has a lot of structure. It's not really random. So here we have some results for the traffic where you have which destinations communicate with which sources. And you see, for example, in this application, which is one from oceanography, an application from oceanography, you see that you have a lot of locality in the sense that each processor has to communicate only with his two neighbors for the application to run, which means that even a topology which, for example, a ring topology, a very simple topology will do for this application, because if you just need communication with two nodes, with two neighbors, a ring is enough. But this is another application here that has to do with solutions of linear equations, where the traffic pattern, you see that there is a lot of locality, so it is a lot of traffic around the diagonal, so each node communicates mainly with his neighbors, but also there is traffic outside, so everybody communicates also with much more distance nodes, with all the nodes, but in a less data-intensive way. Okay? So in this case, this means that it will be important to have a topology that has a short diameter, because you may have to communicate with distant nodes, which means that you will have a topology that requires a large degree. Okay, because to have a small diameter, you will have to use a large degree. Well, this is another application, some variation of the Fourier transform. Here you see a lot of traffic, no locality at all. Actually, you have global communication, very data-intensive communication, even for distant nodes. So here, this means that this is, in this case, the bisection width is going to be the important criterion that's going to be the bottleneck for this application, because everybody, you have uniform traffic, equally intensive between all pairs of nodes. Therefore, it's some cuts that are going to describe how much you can get from one side of the network to the other. This is measured by the bisexual width. Another important criteria for a topology is how well they execute certain communication, prototype communication tasks. Especially in high-performance computing, there are some tasks that arise very often in applications, and we call this task prototype. Okay, so for example, you may have a matrix which is, may have a 10,000 by 10,000 matrix, which is stored by rows in a parallel machine, so that the processor I stores the ith row. Now, if you want to transpose this matrix, then this means that each processor I will have to send each entry to processor J, and this will happen for all processor I and J. So this means that you're going to have a very intensive communication patterns, and this is called the total exchange prototype task. And if your topology is not designed to efficiently execute such a task, then it will not be able to execute any numerical algorithm because the transposition is a very frequent task. Or you maybe want to solve this linear system, x equal to ax plus b, where x is a vector. So, or you may want to find more generally the fixed point in this iteration. And one way to solve this equation is to solve it iteratively, so that you have this vector x, and you have each processor I store and update the ith entry of x. And now, in order to compute the ith entry of x, what you need is to know, the ith row of A, which is fine, but you also need to multiply with all the other entries of x. And this means that the other processors have to send you the entries of x that they compute. Or in other words, after each iteration, t, every node has to send to every other node each new value, okay, which is a broadcast, but a broadcast, multi-node broadcast, which is executed by all the nodes. Okay? Again, this is a very high intensive, communication-intensive task, and if your topology cannot execute such a task efficiently, even if its diameter is small or whatever, it may have many other advantages, but if it's not good for executing the prototype tasks, then it will not be able to be used to be an efficient topology. So one criteria is, for the prototype task, how each topology executes them, how efficiently. Now, this is for high-performance computer. For data centers, the situation is much more random. So usually here you have an environment where you have a great mix of applications, very different traffic patterns. When you combine all these traffic profiles, you cannot really see any good structure that can be exploited. And the only thing that you see is that, in general, there are on-off patterns where some processors communicate during some time, and then they are silent. There is no communication for other prolonged periods of time. And there is a heavy-tailed distribution for the on-off periods, in the sense that there are many short communications, and there are also, however, some very long communications between processors. So this in terms of the traffic profiles. Now, to go to the optical interconnects part. As Bert Offrein described in his talk, there is a trend these days towards using optical interconnects, optical communications for shortest distances. Okay, so some years before it was considered efficient. I mean, you would use communication optical communications if the distance is above 1 kilometer. Then they proved that it is cost efficient to use optical communications if you are at a distance of more than 100 kilometers. Then this threshold became 10 meters. So you could have interconnection between racks. And now it's becoming 1 meter. Probably it's going to become this cost-effective threshold 10 centimeters, and even smaller. So the trend is to have optical communication replace copper communication over shortest distances. And so probably the current situation is, as Bert also described, the situation where you have optics arrive up to the board, but then people thought about, okay, putting the optical fiber arrive at the chips probably, and maybe replace the optical fiber by waveguides, as Dimitris Tsiokos described before, and maybe also around 2020 have optical communications also within the chips. So the idea here is to bring communication closer to home. It's the same thread that exists to the fiber to the home, trench, etc. Fiber to the curb, fiber to the cabinet, fiber to the home. You want to, because the B times L product for copper communications is finite, you want to, in order to increase B, the bandwidth, you want to decrease the distance L over which you use the copper. So this means that you want to put fiber closer to the home, and here the home is the processor, okay? So we're going to get closer to the chip and finally probably all the way to the processor for the optical communications. Now, the architecture and topology design issue here then becomes the following. Okay, you have some nodes, and the nodes here are going to probably be a router and some opto chips that are connected to the router. And so you want to see how many opto chips I'm going to connect to each of these routers. Is it going to be 1? Is it going to be 5? Is it going to be more? What? What is the number, the optimal number? And then these nodes, these routers actually, are going to be connected to each other. And the issue is what topology should they use when they're connected to each other? And how many channels should the routers use in between them in order to, so how many routers or nodes you're going to put on a board, and then you will have to put the boards on the backplane, how many boards to put on a backplane, and what is going to be the interconnection on the backplane for the communication between the boards, and then the system level architecture, where you have the different racks and what will be the topology of the overall system. So these are you have a lot of degrees of freedom about the number of, as I said, of hosts per node, the number of nodes per board, etc. And the number of channels that are allocated for each pair of connection, and how many channels have to go off board or between off rack, etc. And an important thing here is also, okay, after you decide who is connected to whom with how many channels, you have to decide about the layouts, because the layouts, how actually is going to be the waveguide going to be routed on the board. Because the waveguides also take some space, and this space that they take may be important compared to the rest of the space taken by the nodes themselves. And in some cases, the wires or the waveguides may take more area than the nodes themselves. Okay? And this depends, of course, on the topology, because some topologies take more area to lay out than others. So we want to find the efficient layouts and take the layout area into account. And also other issues that have to be decided is whether you use packet or circuit switching. And this is also an important thing. I'm not going to touch on that today. Also, how to use WDM to increase your multiple wavelengths within each waveguide to increase your bisection width and other properties of your topology. So these are the architectural issues that are of interest. And in the remainder of the talk, I'm going to focus mainly on the board level, optical PCBs. And so we take a bottom-up approach, and we're going to look at the board level which, at this point. And the idea here is that we want to look at the layouts that we are going to use, and make decisions about the number of modules that you put on the boards. And of course, this is going to be, when you decide this, you're going to be have an upper bound on the area that you can take. This area will be taken by the modules themselves, but also from the wires, also from the waveguides. So this is going to determine which topologies are feasible and which are not. But for feasibility, you also want to be physical feasibility in the sense that the losses are kept under control, etc. So depending on the topology, the number of bends of the waveguides, of the crossings, or of the length of the waveguides is going to be different. And each of these has some penalty in terms of losses. And you want the topology to be such so that the total number of combination of the total number of bench crossings and their corresponding lengths is below, okay, the corresponding losses actually are below some threshold. So the idea is the following. Each node is actually, by node I mean that it is a router, and each router is connected to some chips that contain the processor and the memory. And we want to decide how many of them are connected, and then the routers, what is going to be their topology, and the layout of the waveguides. For example, okay, the corresponding problem exists in when you have also electrical interconnects, and there people have proposed the so-called Thomson model, where the idea is that okay, you have 2 dimensions on which you can use to lay out everything, and therefore you put these are the nodes, which include probably routers and the hosts. And then you lay out the wires in tracks, and you can have either horizontal tracks or vertical tracks. And because this is electrical interconnects, these crossings are not really permitted, because this will be a short circuit. Therefore, you use one layer to lay out the vertical wires, and one layer to lay out horizontal wires, and then you use vias in order to connect one layer to the other. And you can imagine, so this is actually a 3-dimensional mesh laid out in 2 dimensions, because if you go to richer topologies, you will see that most of the space taken here will not be the nodes, but it's going to be the wires. So people may use more than 2 layers in order to reduce the total area taken, the real estate taken by your design. So in electrical interconnects, this is how you do it, and you use multiple layers whenever there is a crossing. Now, and here are some examples, okay, for electrical layouts of a 3-dimensional mesh. And, this is a collinear layout in the sense that all the nodes are in the same line, and, of a 3x3 torus. And this is a fully connected network, so everybody is connected with everybody else, and it's a collinear layout. So you can have a 2-dimensional collinear layout. Now, when you go to optics, there are some differences. One of the differences, first, that an important thing is that the wires, the waveguides, cannot really take an abrupt turn, 90-degree turn here, but they will have to, it will take a lot of space whenever this wire makes a bend, okay? And actually the radius of the bend is going to affect a lot the losses that you get, but also it's going to affect the area that is going to be taken by these waveguides. So one has to do with the bends, which is an important difference. Another difference is that in the optical domain, you can have waveguides cross each other. So it's allowed. There are some losses, of course, because of that, some crosstalk because of that, but it's allowed. So you do not have to really use multiple layers whenever a horizontal wire crosses some vertical wire. And also, these crossings do not necessarily have to be at 90 degrees. You can have also, so you do not have to have only horizontal or vertical. You can have 60 degrees, 90 degrees, 30 degrees angles, and you may have a richer topology because of that. Different, however, angles of dissection will result in different crosstalk, different losses. But it may be worth using different angles, different than 90 degrees, because the benefits may outweigh the disadvantages. Okay, so this is a strategy that one could use if we go to optical PCBs, and this is the strategy that we have used in the tool that we have developed. Here, in this, for the time being, we allow only 90 degrees tracks of 90, that intersect at 90 degrees. And you place the nodes along a two-dimensional mesh, and you reserve some space here below each of the nodes for off-board communication. So this is going to be taken by waveguides that are going outside the board to the backplane and to other boards. And this is going to be taken, this space here is going to be taken by rows, by waveguides that go in the horizontal direction. And you have waveguides, this space taken by wires that are going in the vertical direction, and here also. And so this is, the total area taken is going to be the area taken by the nodes and also by the different waveguides, horizontal or vertical or off-board. Now, the different waveguides will have there will be some separation rules that depend on this bending radius R0. So here, this bending radius takes you, it's an important parameter, and so this is one of the parameters, that there will be a separation of R0 between bundles of waveguides that they want to make a common term. And also, another thing is the crossing angle. So you could reduce this R if you allow some waveguides to intersect at less than 90 degrees. You're going to have more losses because of that crosstalk, but you will decrease the separation between different waveguides, therefore decrease the total area. Okay? And this may be beneficial. And another thing, okay, in this picture, I have that each node is a router together with the opto chips, but this also has some internal interconnection because the router and the opto chips by themselves take some area also. Okay, so depending on what is the number of pins and the distribution of pins around the router, because in this case I assume that the pins exist in all directions, in all four sides of the router. You may have the router being interconnected with these are the processors, with the processors using a topology like that, in which case the node will take a certain area, or if all the pins of the router exist on one side only, because this may be a constraint, you may use a different topology that takes a different area for the node. Okay, so this is, we have designed a tool that takes this into account to design actually topologies and calculate losses, calculate areas, bisection width, and all these parameters. We're starting to get some results. I'm not going to go much into the results, but just to mention what type of results one can expect. So here we have assumed for the tool as input we have used the parameters of the Foxtrot project. So the baseline is that the chips have these dimensions. The bending radius is this. We have assumed crossing angles only of 90 degrees. This is the area taken by each node. And we want to have this system on the board. So this is the total layout area we need. And here we see what will be the benefit, what would we gain if we get better topology in terms of the size of the chips. So if we have better chips, we could reduce, let's take less dimensions. We could reduce the layout area by 53%. What would be the benefits of going from this bending radius of 20 millimeters to 10 millimeters? You can see that in that case, you could get 23% benefits in the area, or if you make your radius even better, you could obtain much more benefit. So this means that all these topologies are not only constrained from the size of the chips, but they're constrained also from the bending radius. And also, if you use the different angles, crossing angles, you could get better layout areas. So this proves that one has to take the layouts into account when designing the topologies, because the layouts, their parameters, play a big role on how much you can fit on each of the boards. So we have currently, okay, so this is how the tool works. You put some physical layer specifications. What are the footprints of the chips? What is the pinout, the board size that you have? Is it an A2 or an A4 size? What are the traffic demands? How much, for example, how many flops are your chips? How many chips? Then use a rule like the rule of Offrein referred to for converting computation to communication requirements. You have some budget that you have as input, and you also have some performance that you want, which we express in terms of the bisection width. And then we generate topologies, different topologies, by exploring all different variations, all different choices. All of these topologies have to be feasible with respect to the power budget, the losses, etc., and the bisection width that you require. And then from the topology all feasible topologies, we take the one that has the most, allows the most nodes to be placed on a board. So here are some of the results. So here, for example, you can get different results for the number of hosts that you can put on a board. This is as a percentage of the traffic that goes outside the board. Actually, this percentage of the traffic really reflects the total size of the system, in the sense that when you have 0 going out, this means that the board is your system, while if you increase the percentage of traffic that goes to the outside world, this means that this board is part of a larger system. So the size of the total system is taken into account indirectly through this parameter, and because, of course, the size of the total system is going to affect the off-board communication channels that you need, etc. So for different total sizes of the system, you get different topologies for the board that are optimal, etc. Or you can see what is the effect of the board pinout. Depending on the board pinout, different topologies will become optimal. How do the results change when you have a board which is larger? Instead of an A4 size, you have an A2 size, and things like that. So to conclude the talk, what I have described is that, first of all, I argued that, what is well known, that optical interconnects are going to be deployed over shorter and shorter distances. They're going to soon come on board, and probably on chip in the next 10 years. I believe that optical interconnects will require the revisiting some of the architectural issues, because the answers, the solutions of the past may not be the best solutions when you go to optical interconnects. Especially the layout problem is significantly different than in the case of electrical interconnects, and because the electrical layout models is what affected actually the main topologies for the electrical interconnects. When these layout models change, I believe that the topologies that are going to be optimal for the optical interconnect case are going to be very different than those that were optimal in the electronic case. We proposed a possible layout strategy for optical boards that generates automatically topologies and checks for the physical parameters to be under certain values, losses, etc. And it calculates the feasible designs and selects the optimal one. This is a first step that we have taken, but there are many future steps that are required. So we have here the effect of the bench, etc., but we do not have how the dispersion models for the dispersion. We do not have not examined different waveguide materials. Of course, these are going to be just parameters in the model. What I described was for direct topologies, but what about indirect topologies like fat trees? What about topologies that use buses, where you have a bus, where many, instead of point-to-point links, you have buses where you have many nodes that are attached on a given bus, and how things are going to be affected by WDM, etc. So these are things that we plan to explore in the future using the tool we're developing. So that's the end of the talk.
So the speaker is now open for questions. Any questions? I have one question. What are the factors or the applications that will eventually define if packet switching or circuit switching will be deployed?
Yeah. I think that, okay, in order to establish a circuit between two points, okay, two processors, this means that these two processors will have to exchange significant data among themselves. Okay, if it is just a little bit of data, its packet switching will be optimal. But if there is some traffic stream that is going to, traffic flow between them that's going to last for long, then you should use circuit switching. Okay, so this is the idea.
So it's pretty much like in optical communication networks.
Pretty much like that. Yeah. But and you are going to have both sporadic traffic, and you are going to have a long-tail distribution also, some flows which have big durations. I mean, we know it. Now, what will be important is how to predict things, okay? Because you want to predict the duration of the flow. After it has finished, you know it. But that's not, you have to know it, to predict it in advance in order to establish a circuit and gain the benefits. So I think it will depend a lot on the prediction algorithm that you get, how effective you are going to be about this. Okay.
Any other questions? No? Okay, then we're ahead on schedule. So, but in any case, I suggest we have a half an hour coffee break, and then we can go on with two remaining talks into today's session. Okay, after a rather long coffee break, it's time to start the session. Our next speaker is Bakopoulos from the National Technical University of Athens, and he will talk to us about active optical cables and advanced multiplexing techniques.
Hello, thank you for the kind introduction. Hello, everyone. I'm glad to see that everyone is here after the coffee break. So my name is Bakopoulos. I'm a researcher at the National Technical University of Athens, and for the following about 60 minutes, I will talk to you about active optical cables and advanced multiplexing techniques. So this is the brief outline of this presentation. So I will start with an overview of of the topic of the area of active optical cables, so that I can acquaint you with some recent developments and the general trends. And then I will try to answer the question, why do we need multiplexing, first of all, in active optical cables? And once I convince you about that, we will see what types of multiplexing we can use in active optical cables and people are using. And I will end with with an outlook, some suggestions for further, let's say, exploiting the concepts of multiplexing in more advanced network concepts. So starting with the overview, I will start with, let's say, a fundamental question: why optical interconnects? That was, I think, that question was very well answered in a previous presentation by Dr. Offrein earlier today. So I will just very briefly show you this schematic here, which summarizes actually where optics make sense. This is the optics realm, this whole area. And what's good in optics is that they give you a very good bandwidth times distance product, and this is where it beats copper. Copper can be cheap, copper interconnects, electrical interconnects can be cheaper, but optical interconnects beat electrical interconnects in terms of bandwidth times distance. So if you need long distance or very high bandwidth or a combination of both, then it's like a one-way solution. Now, together with this good performance, you get some additional benefits by using active optical cables, like a lower total cost of ownership, reduced power, and increased density, as it was already pointed out by several speakers today. So what types of optical interconnects are there? We all know that there are optical interconnects in high-end applications like high-performance computing or data centers, but they are also being introduced very fast also in consumer electronics. This is some examples like the light peak or some very fast HDMI cables. Of course, the rest of this talk will focus on the more high-end applications like interconnects, HPC, and data centers. Of course, high-end doesn't mean also high cost, necessarily. So this is how an active optical cable looks like. It has been already described. I think what is really important here in the active optical cable is that it actually has electrical interfaces at the input and output, and that helps very much for the robustness of the solution. It's very easy to handle it in the field, and very straightforward, and a very straightforward way in order to pay as you go. For example, to upgrade your capacity right when you need it. So you pay for your transmitters and receivers when you really need them. So there are several types of these receptacles, of these connectors. Here is an overview of some of the most widely found in optical interconnects. The ones that are closer to the high-end applications that we are talking about are the SFP, the small form factor family that are shown here. The SFP, the QSFP, which is actually 4 SFPs in a single connector. CXP, which is 12, and a most recent standard that is the CDFP standard that packs 16 transmitters and receivers in a single package. And the purpose of this is to achieve 400 gigabits per second capacity on a single active optical cable. And these are some examples, some very, very recent products based on this CDFP MSA. These are two, let's say, characteristic cases. One has been introduced by T-Connectivity. This is based on 850 nanometer VCSELs. And the other one is based on silicon photonics. It's been showcased by Molex, ex-Luxtera in the US. And this one is based on 1550 optics. So it's based on an external laser and silicon photonics. This is actually how the older QSFP package looks like. but it gives you a good overview of how it is inside. And talking about what's inside an active optical cable, this is a block diagram that shows us more or less what you could find for each of the parallel lanes, for each of the parallel channels that you can find in an active optical cable. So, as you would expect, we will find the optics, like a VCSEL or a laser source, and the photodiode. But apart from this, there is also a number of electronic components. It's the VCSEL driver, clock and data recovery, circuitry, amplifiers, and in many cases there is also equalization circuits. And these equalization circuits are necessary for signal conditioning, especially if we want to increase the data rate by more than 10 gigabit per second. So if you want to go to 28 gigabit per second as the latest products, then you need to do some signal equalization at the input, even at the input, in order to compensate for parasitics and for degradation of the electrical signal at the electrical contacts of the package. This is actually one of the big challenges in active optical cable, the electrical signal integrity. And the second one is the front panel density, the aggregate bandwidth that can be handled within for example, within a switch with a 1U size, within a 1U rack form factor. So this, for example, shows that if you use the CDFP modules, you can fit 11 CDFP modules in the front panel of a switch, for example, and that should be able to handle 4.4 terabit per second. And this is very important because the equivalent number, if you were using QSFP form factor, would be 3.6 terabit per second. So you have an over 20% upgrade in the front panel density. This is a big concern. Another big concern that I already mentioned is the signal integrity, the integrity of the electrical signal, and that has been already pointed out by the talk of Dr. Offrein earlier today. So when you scale the rate, the electrical signal integrity is compromised, and this creates the requirement for more equalization, and more equalization and regeneration of the signal means higher power, more components inside the package, more cost and more heat. And a potential solution is the midboard optical modules. It has been already discussed here that, okay, this is how the active optical cable solution looks like. So imagine that you have an ASIC that generates traffic, and you want to interface it to the outside world. So you put in your front panel the transmitter and receiver in the form of an active optical cable. Of course, the electrical signal has to propagate throughout all this length. So you can bring your optics next to the ASIC with a midboard optical module, or in an even more forward-looking approach, you can put the optics inside the ASIC. Especially the midboard optics is something that the industry is really looking currently. There are, of course, several concerns, several thoughts about the reliability and how practical it is, because, for example, if an active optical cable fails, then you can simply take it off and put a new one. But if a midboard module fails, then it's not that simple. Anyhow, there is already a wide range of midboard modules available. This is, for example, one of the quite well-known types that is around for some years, the SNAP12 module. These are some, let's say, state-of-the-art specifications, and these are also some quite well-known products that have been. The Avago micropod is a quite well-known product that has been around. So you can see here in the figures how it looks like, the size of it. It also uses 850 nanometer VCSELs, and for the electrical contacts, it's using a micro LGA attachment. And this is taken from research. This is also well-known work with a big impact from IBM. the Holley optochip, because it actually has holes in this substrate that is used to mount the photodiode in the VCSEL. And using this Holley optochip, it has been demonstrated 24 channels at 12.5 gigabit per second over multimode fiber, and the same technology has been demonstrated up to 36 gigabit per second. So it's the midboard modules are already a growing, let's say, solution and technology, business, what have you. So from this very fast-forward, let's say, overview, it's getting, let's say, clear that in the field of optical interconnects and active optical cables and their derivatives, there is a large technology quiver that is available. And that can be, for example, VCSELs, silicon photonics, established technologies in the datacom sector. Most of them are multi-mode centric. Some established technologies coming from the telecom segment, which are more single-mode centric, high-speed electronics and advanced packaging techniques. And this set of technologies has to meet the requirements that are posed by the application. And these are not, this is a mixture of performance, power, cost, reliability, feature set, and customer requirements that are potentially introduced by the customer. So the exact mix and the exact proportion of these requirements are not always the same. So, for example, in the case of high-performance computing, it might be more crucial to have low latency rather than very low cost, which in the case of data centers would be probably the other way around. So we can say that there is no one-size-fits-all here, and the application requirements are what indicates the optimum solution. So, as an example, there is this the debate: is silicon photonics more appropriate? Are VCSELs more appropriate for optical interconnects? As you can see here, VCSELs are typically more efficient. Multimode VCSELs can minimize the cost in the case of very short-reach connections. On the other hand, silicon photonics with an external laser can aim at longer reach, and also silicon photonics appears to be, quite appropriate for chip-to-chip interconnects, because silicon photonics is supposed to be, the whole target is to make it CMOS compatible. So it kind of makes sense to apply it for on-chip or chip-to-chip interconnects. So a similar argumentation can be made for the debate single mode or multi-mode. So with single mode, you can have longer reach, you can have compatibility with actually all the prominent photonic integrated component platforms like silicon photonics, indium phosphide, or glass. And of course, single mode fiber is cheaper than multi-mode fiber. But on the other hand, in the case of multi-mode fiber, you can have more relaxed assembly tolerances. So this means cheaper assembly. You can have, and also typically the PCBs are multi-mode. So yes, again, there is no single solution for everything. Let's see now, why do we need multiplexing? We are definitely all aware that the amount of traffic, the amount of global traffic is booming, and the reason is that we are storing everything in the cloud. We are logging into our Facebook accounts every day, every hour. So this is pushing traditional optical interconnect technologies to their speed limits, and so far scaling the capacity has been done using a simple recipe: increase the number of parallel lanes and increase the line rate for each lane. And let's say an extreme example of how this could be scaled is shown here. It is actually the outcome of the Policies project, which ended a few months ago. So this project developed a transmitter for 100 gigabit per second. And how did it make it? By using some top-of-the-line technologies, actually the top-of-the-line available technologies to do this. And that was, in this case, a polymer modulator, externally modulating a DFB laser, some indium phosphide electronics, driving and multiplexing the signals inside the package. And with these technologies, it was possible to develop this very impressive result and achieve transmission over more than 1.5 kilometers of single-mode fiber. And of course, according to the recipe that I mentioned, you can easily continue scaling by adding an additional channel. So this is the example of a 2 times 100 gigabit per second transmitter that will be published soon. But what does this example tell us? It tells us that it is possible to continue scaling using this recipe, this traditional recipe. However, in order to do this, you have to use the top-of-the-line technologies, and it is quite likely that the top-of-the-line technologies will be also rather expensive, and that could be okay, that would be acceptable for some applications, but not for all. So in order to reduce the cost, you should be able to exploit more, let's say, well-established technologies. So, for example, these are some targets for the cost and the power that are taken from references from the industry. So the current target for the cost is $12 per gigabit per second, and the target is to reduce it by 25% every year. The same goes for the power. So the current power is 30 milliwatts per gigabit per second, and the target is to bring it down to 5 within the following few years. Now, in the case of the 100 gigabit serial transmitter that I showed you earlier, this power is about 80 milliwatts per gigabit per second. So it kind of shows that an alternative path is necessary. And this alternative path can be multiplexing, because it can relax some of those requirements. So the question, of course, is what multiplexing? So I will be talking about 3 different multiplexing types. The most prominent and the most researched so far: wavelength division multiplexing, space division multiplexing in multi-core optical fibers, and multi-level modulation. And I will try to make their fast, let's say, profile, the pros and cons of each one. So when it comes to WDM, it's a big advantage that the multiplexer and the demultiplexer are passive components, and it's scalable. It has been actually proven very well in the field of telecommunications. So it is definitely proven to be scalable. It's possible to transmit tens or hundreds of wavelengths in a single fiber. Of course, the main, let's say, drawback is that WDM lasers are not a commodity yet, especially not at the price that would be appropriate for optical interconnects. In the case of space division multiplexing, a big advantage is that multi-core fiber is smaller. It can be potentially cheaper than a fiber bundle. Plus, no specialized active components are necessary, so you don't have to develop a new cheap laser. On the other hand, you have to develop, you have to make actually the multi-core fiber chip, and the coupler that couplers the light into the multi-core fiber has also to be made cheap. When it comes to multi-level modulation, it's a really big advantage that no specialized optical components are necessary here. So in order to introduce multi-level modulation, what you actually have to do is more focus on the electronics. And this actually is a good argumentation that multi-level modulation can have a faster time to market, because it's typically easier to develop and introduce a new electronic technology. A big drawback is that, of course, we need to have these linear electronic components, and the additional cost and power consumption that is associated to these new linear components. Plus, on the other hand, when you are applying multi-level modulation, this means that you have a tighter loss budget because of the fundamentals of modulation. So, to conclude, yes, again, there is no one-size-fits-all solution. This can be a very good take-home message from this presentation. The optimum approach depends on the application requirements and the available technology, the currently available technology. So you have to, let's say, tailor your design in order to push the performance envelope on a case-by-case basis. And for this reason, we need to have photonic technologies that enable multiplexing in optical interconnects. So going into some more detail about each one of these multiplexing technologies, and starting with WDM. So this is a very interesting research from Google. So it actually compares here the cost of a traditional VCSEL, multimode VCSEL-based link, which is shown here, versus reach, and compares it to the cost of a link that is based on a DFB laser and single-mode fiber, which is shown here on this dotted line, and to the cost of a WDM solution. And this is represented by these two dashed lines. They have been calculated with different assumptions on the cost of the WDM components. So what this research tells us that the WDM gives better price per meter slope. So the slope is better. It's 20 times lower than single-mode fiber, 10 times lower than single-mode fiber, and 20 times lower than multi-mode fiber. The reason is single-mode fiber costs less, and with WDM you need less fiber. So for longer reach, it's becoming clear that WDM can cost less. Now, taking this concept a step further, this study here extrapolates the bandwidth requirements of an active optical cables based on the rule that is very often, usually followed by the industry, where it goes that the next generation of one technology has to provide 10 times the bandwidth of the previous with 4 times the cost increase. So by using this rule and extrapolating the performance of the WDM links here, you can get that you can have a cost advantage even when you're using short reach. These graphs actually here show the point where WDM has the same cost as the traditional multimode VCSEL solution, and it can be as slow as a few tenths of meters, as small as a few tenths of meters. Of course, there are still challenges like scaling size, power, and cost. So one of the probable challenges when it comes to WDM is how do you generate the signal? In datacom, the main workhorse for signal generation is VCSELs because they have a large number of pros, so like reliability, low power consumption, and actually VCSELs have been shown to achieve pretty fast performance, like 56 gigabit per second with a multimode VCSEL, or 40 gigabit per second with a single mode VCSEL. These are really impressive results. At the same time, WDM operation has been demonstrated with VCSELs. So for example, this is a 4 times 14 gigabit per second VCSEL link. So the big challenge here is how do we combine them? How do we make these very, very state-of-the-art fast VCSELs also WDM? And this is actually one of the targets of the Mirage project. And I won't go into more details because there is a talk on Friday by Professor Ralph Meyer, so he can actually answer, I guess, all your questions on the VCSELs. Another option for WDM generation in active optical cables is external modulation of a CW laser. This is the approach that is followed by Molex now, and a similar approach has been also applied to a polymer board by HHI, either by butt coupling a DFB laser or a gain chip in order to make an external cavity laser. Okay, so these are the main approaches for the generation of the WDM signal. And to my understanding, in the next talk, in the final talk for today, we will also hear about the possibility to have indium phosphide on silicon, which is also a very interesting option. When it comes now to multiplexing and demultiplexing the WDM signals, what are the solutions? So what has been originally applied is a micro-optics assembly, like this shown here, using micro lenses and mirrors and WDM filters. Of course, this involves multiple alignment, multiple levels of packaging, and this actually leads to high assembly costs. Another option is to do a hybrid assembly on a PLC, like it's shown here, like putting a thin film element inside the trench in a polymer board. This is definitely simplifies. It reduces the levels of packaging, but again, some assembly costs are involved, and this is why people have been looking into integrated photonic solutions like silicon photonics, for example, and there are a few options for this, a few designs for this, like arrayed waveguide gratings that are capable of achieving a flat spectral response, and they are rather simple structures. The main drawbacks here is that the long path lengths makes them quite sensitive to the phase noise of the waveguides, and also create some temperature dependence. Another very interesting option is using ring resonators. This is actually a solution, a very interesting solution, because the design can be very easily tailored. You can see different designs achievable by different configurations of ring resonators. It can give high extinction ratios, small footprint, but on the other hand, we're talking about a resonant structure, so these are even more sensitive to phase noise, and they have an even higher temperature dependence, which is good if you want to have a tunable filter, but not good if you want to have an athermal filter. It is, in principle, it is possible to make an athermal design here, like also for the AWGs, but it also introduces some complexity in the fabrication. Another option is to use a cell grating, which is a more insensitive solution, a more insensitive design to process variations. On the other hand, it involves some challenges when it comes to the fabrication of the diffraction grating faces. Nevertheless, there are some very interesting results coming from either from a silicon nanowire platform or from a micrometer SOI platform. Now, of course, one known issue of such integrated filters, especially when they are made in nanometer SOI platform, is polarization issues, and these stem from waveguide birefringence. So one potential solution that is being investigated within the Mirage project is to design a dual polarization filter by using a simple dual segment design of an AWG. So we are engineering the waveguide geometry so that by using two successive segments of different waveguide design, the overall group index for the T and the TM polarization are the same for a range of wavelengths. So with that way, it is possible to make a polarization insensitive device, and by putting also some individual heaters on each of these sections, it's possible to tune the T and the TM response individually, as can be shown here in these results. Another option in order to solve the polarization issues in the so-called thin SOI platform would be to use polarization diversity. So you can split the two polarizations of the signals using, for example, a 2D grating coupler, and follow the same type of filters for the TE and for the TM paths of the signal. So you have a filter here for the TE and a filter here for the TM. This is to some extent advantageous because you can generate here the optimum design for each polarization. On the other hand, it kind of needs double the real estate that you would need if you were using a single filter. And of course, it is also based on the 2D grating coupler, and it also carries with this all the let's say, challenges of using a 2D grating coupler, like the wavelength dependence or the insertion losses of the 2D grating coupler. Nevertheless, there have been some very interesting works like these two shown here. When you can see here the 2D grating coupler and the polarization diverse paths that end up to the same photodiode, for example. And these are quite promising results that actually prove the feasibility of the concept. Now, moving on to multicore fibers. Why should we use multicore fibers? I think this schematic here gives us the answer. It's quite straightforward. So this is the size of a single-mode fiber. This is the size of a 7-core fiber. And this is the size of a 19-core fiber. As you will notice, they are exactly identical. So if we introduce multicore fibers in optical interconnects, what we can do is dramatically increase the bandwidth density, or equivalently, dramatically reduce the size, which is good in terms of cable managing or ventilation or even cheap real estate when we want to address chips. And potentially, we can also have low cost for these fibers, because there's no real reason why they should be more expensive. There are no sophisticated fabrication processes involved. So the first question that comes to mind is, are there any good quality multicore fibers available? And the answer is yes, and they have been single mode and multi-mode fibers, multicore fibers have been fabricated and have been validated in transmission experiments that confirm their suitability for telecom and datacom, of course, applications. The main outstanding concern here is the cost. And the cost depends on the demand, of course, and the demand in turn depends on commercial adoption of the concept. So it's sort of a chicken and egg problem, but in principle it is very likely that these multicore fibers can get quite as cheap as a traditional single-core fiber. Now, when it comes to interfacing the multicore fiber, there are quite a few solutions around. First of all, multicore fiber connectors. Here are two examples taken from Furukawa and Sumitomo. The main challenge here is the angular precision. It has to be approximately +1 degree. Interfacing the multicore fiber is also done with multicore fiber fan-outs. So these fan-outs split, let's say, each of the cores in a multicore fiber into separate individual single-mode fibers. And let's say the most straightforward way to do this is by using a collimator at the edge of the multi-core fiber, and the microlens array that is then attached to each of the fibers. Of course, this is quite an expensive solution. Another solution that has been proposed is this from Fujikura, which is based on inserting small diameter fibers in a precisely machined V-groove array, so that they have the same arrangement with the cores of the multicore fiber, and then simply attaching them back to back, like butt coupling them. Another more advanced approach is this one shown here. It's laser inscription of three-dimensional waveguides in glass. So you can actually write the waveguides by using a femtosecond laser, and you can define the exact position of the waveguide. So you can actually match the arrangement of the cores in the multicore fiber here, and then just end up with a planar arrangement on the other side. And this has been shown to be, it's customizable to the fiber geometry, and it is already a commercial available solution. The next level would be to actually interface a photonic integrated component directly with a multicore fiber. That would be actually very nice, because you can really reduce the chip area instead of using a fiber array with a much higher pitch between the cores. One nice example is shown here. It was published a few years ago. So in this example, what was done is actually a VCSEL array was fabricated following the exact same geometry of the multicore fiber. And by simply attaching the multicore fiber, it was possible to route each of the VCSELs into an individual core. This works. Of course, it involves some challenges, like, for example, you need to make a custom design of the VCSEL chip so that it matches the specific multicore fiber that you are using. And of course, it needs precise angular alignment of the fiber at the assembly side, which is not a standard. Actually, the same solution has been proposed and has been demonstrated in order to address silicon nanophotonic chips. But you can use grating couplers, 1D or 2D grating couplers, and align each of these grating couplers to one of the cores of the multicore fiber. This is good because you can reuse the existing libraries of the photonic components that you have. It definitely involves some lithographic challenges when you want to put many grating couplers one close to the other. And again, of course, it kind of depends on the actual, let's say, fundamental limitations of a grating coupler. So if this is a problem for a particular application, then okay, it's probably not a good solution. So how about in-plane coupling of the multicore fiber to the photonic integrated circuit? Well, this actually involves a couple of steps or a couple of challenges. It's not quite straightforward. The first obvious challenge is that the multicore fiber has a circular arrangement of the cores, whereas the photonic integrated component can only have a planar arrangement of the cores. So the first thing that you have to do is to convert this to this. The next thing is that you will also need some extreme mode conversion, because in this schematic, if this is the size of the core, of the fiber core, this is the size of the SOI waveguide. So it's kind of extreme mode conversion required. And I will just show you very, very briefly some of the work that we are doing in Mirage in order to address this issue. So we're starting with the single mode fiber core, and then we're using a multicore fan out like the one that I described to you a few slides ago. And this is used in order to change the core arrangement from this circular to a linear core arrangement, and also to do some small tapering, some first step tapering. And then as a second stage, we do the second stage tapering using a silicon spot size converter based on a polymer material on top of an SOI board. And so we do here the second stage tapering and the coupling to the silicon wire. I won't go into much detail here because you can see all of the details tomorrow at the poster session, and you can ask my colleague John Poulos. I will just mention that the theoretical coupling efficiency is 1.73 dB for TE and 1.78 dB for TM, showing a quite good polarization insensitive operation. Now moving on to multi-level. Why multi-level? As I already mentioned, it's a straightforward increase in the per channel bit rate, so you don't need any special optics, any development of special optics. You don't have to increase the bandwidth requirements. By using lower electronic rates, you have lower cost for the electronics, lower consumption in principle due to the lower rate, no need for extreme multiplexing, ETDM multiplexing at the serializer, deserializer. At the same time, you are using lower rates for the optical components. This means that you can directly use the existing components. You don't need to develop ultra-fast new transmitters or receivers. You can mitigate all the packaging concerns by reducing the electronics rates, the line rates, so you don't have the signal integrity issues. And eventually, by merging several channels into a multi-level channel, you can also use less optical components eventually. And this is important because, as you can see, the optical part, the optical sub-assembly is a good portion overall cost of the overall bill of materials for an SFP pluggable. And you can see actually here how by using different, more complex modulation formats, you can gracefully upgrade the capacity, the achievable capacity from the link. This is actually an example showing more, let's say, vividly what happens. I will actually skip this slide because I think we are quite running out of time. I will just mention that, okay, despite this very impressive potential for multi-level modulation, nothing comes for free. So you can definitely upgrade the capacity, but as you can see here from this is taken from the seminal paper of Chambre. You can see that as you increase the complexity of the modulation format, the theoretical SNR at the receiver in order to successfully receive the signal increases. So this means that moving from here to here is equivalent to moving from your bit error rate curves from here to here. So you need much more power at the receiver. This means that you can achieve a tighter loss budget. You can eventually achieve smaller reach, in principle, because of the tighter loss budget. This is actually fueling the discussion for forward error correction in Datacom, which is it has been relatively recently introduced, and it also supports the fact that as you move on to the number of symbols, of bits per symbol, you increase the complexity, you introduce some, let's say, limitations to the link. So it's not something that can be applied as a magical recipe to every link, but it can be applied in some cases and really upgrade the capacity. These are some examples here. So on the left-hand side is an example of using a bandwidth-limited transmitter. So we are using a 2.5 gigabit per second VCSEL transmitter, and we are trying to transmit 4.9 gigabit per second with this. In this case, we are using NRZ on-off keying. In this case, we are using PAM4. So in order to achieve the 4.9 gigabit per second with PAM4, the baud rate is 2.45 gigabit, which is within the 3 dB bandwidth of the VCSEL transmitter. As a result, as you can see here, the eye diagrams are wide open in the case of PAM4, whereas in the case of NRZ, there is some eye closure, and this is also confirmed from the bathtub curves, both for the amplitude and for the time margins. And actually, this eye closure can be quite challenging for the case of the clock recovery. On the right-hand side, let's see what happens when we don't have the bandwidth limitation, when we remove the bandwidth limitation by using a 10 gigabit per second VCSEL transmitter. And we are still trying to transmit 6.25 gigabit per second, which is well within the bandwidth of the available transmitter in both cases. So as you can see, both concepts work error-free, of course. In the case of PAM4, there is a power penalty of 5.9 dB. And this definitely is a concern for the designer of a link. It is something that has to be taken into account for the designer of the link. So the fact that actually in the case of optical interconnects, there's a close interplay of electronics and photonics. This actually leads us within the Mirage project to try to co-develop and co-optimize the electronics and the photonics of the same system to try to develop them hand in hand. So with this way, it's possible, for example, to get rid of the limitation for a predefined impedance level, like 50 ohms. So you can use more custom impedance levels in order to improve the noise performance of the overall system. The main target here in Mirage is to develop 40 gigabaud, to achieve 40 gigabaud PAM4 using single mode 1550 VCSELs. And there are some design challenges that are associated with the multi-level operation, like how do we generate the PAM4 signal on the chip, how do we account for bandwidth limitations of the link, and for this I will show you right away the concept of a feed-forward equalizer that is being developed in the same project. And of course, concerns that are always associated to multi-level signals are linearity at the receiver in order to discriminate the different levels, and the necessity for higher sensitivity exactly because of the fundamental challenges in terms of OSNR, as I mentioned earlier. So this is the example of a PAM4 feed-forward equalizer that is being designed in Mirage. It is actually a two-tap equalizer. This is a block diagram. So it involves a 1-bit delay of the signal and the multiplication with a tunable weight, a digitally tunable weight. And you can see here what happens if you try to modulate a bandwidth-limited VCSEL at 40 gigabaud, and you also have some additional bandwidth limitations due to the interconnects between the VCSEL and the driver. Then what you get is a fully closed eye. So if you apply the feed-forward equalizer, then you can easily open the eye diagram and achieve error-free detection at the receiver. So in the next few slides, I will show you some prominent recent examples of multi-level modulation that have been demonstrated quite recently. This one is a very good example of 60 gigabit per second PAM4 over 1 meter using 850 nanometer VCSELs. That was demonstrated last year. And as you can see, because of the use of multi-mode fibers, the maximum achievable rate rapidly deteriorates as the length of the link increases. Now, what happens if you apply a feed-forward equalizer, a similar equalizer like the one that I described to you? If this is applied both at the transmitter and at the receiver using the same VCSEL, you can actually increase a bit the baud rate and also enhance significantly the achievable distance. So let's say the record here was 64 gigabit at 57 meters. Another very recent result was also demonstrated using single-mode VCSELs. These are some results taken from two recent papers. One was shown last year, and the other was shown a few months ago at OFC. Now, using these single-mode VCSELs, actually an additional level of multiplexing was introduced here. That was polarization multiplexing, in addition to PAM4, to multi-level signaling. And using this combination of the two, it was possible to show 100 gigabit per second, link in two different, let's say, configurations. The first configuration that was shown last year was achieved 100 meters using direct detection, and the second one introduced coherent detection and DSP at the receiver, and significantly upgraded this achievable reach to 400 kilometers due to the capabilities of the coherent detection concept and the DSP. Now, an obvious question is, can we apply more complex modulation formats, even more complex modulation formats to datacom? Well, yes, in principle, it is possible. You can see an extreme example here where OFDM was applied to a VCSEL. The VCSEL bandwidth was 1.7 gigahertz, and by applying OFDM, it was possible to transmit 11.25 gigabits per second at 25 kilometers. This is quite impressive. Of course, everything comes at a cost, and the cost here is transmitter complexity. I don't have to go through the experimental setup, but I think it is quite convincing that it is complex. So the answer to the question is, if we can apply more complex modulation to datacom, it actually depends on the particular application requirements. So it depends on the costs and the size of the optics and the electronics, the tolerable latency, the loss budget. If forward error correction is, if we are eager to apply forward error correction, and actually similar considerations apply for other formats, more complex or less complex, like CAP or like PAM8 or whatever. So now, after let's say describing some prominent examples of multiplexing concepts, I will just go very quickly through the general concept of the Mirage project, and this is because it is a very relevant project that is it's currently in progress. It is actually the strategic target of Mirage is to develop an optical engine that is capable of terabit interconnects. We want to build a terabit active optical cable, and the way that we are trying to do it is exactly as I described in the previous slides. We want to combine WDM, transmission in multi-core fibers, and multi-level formats. And in order to do this, we are developing a 3D integration ecosystem, a complete, let's say, technology ecosystem, and this involves 3D glass interposers for chip to multi-core coupling, an optical nanometers silicon photonic board, 40 gigabit per second VCSEL arrays, WDM VCSEL arrays, linear electronics, drivers and transimpedance amplifiers for the receiver side, plus a set of 3D integration processes that enable what was described earlier by Dr. Tsiokos as the requirement for advanced 3D packaging. And by applying all these technologies and all these concepts, this is our vision, the vision of fabricating a terabit capacity active optical cable using a combination of all these technologies. Given that we have this very versatile toolbox, it is possible to combine these toolbox, these piece parts in a large number of possibilities. So you can have increasing combinations of complexity and functionality on the same chip. So this is actually just an example of what could be fabricated and what we hope that we will fabricate in the next 1.5 years that the project will be running. So finally, some outlook. Let's say some further thoughts on the advanced multiplexing concepts. So a question is, are there any more benefits from multiplexing? Any benefits that were not, let's say, identified so far, that are not very clear so far? Let's try to see, let's say, to imagine how a future data center might look like. And to help us in this, I have included here a proposed architecture, a proposed network architecture called Mordia. This was developed a few years ago in the US. And this research effort here is actually in line with a large number of projects and some good research, let's say, efforts worldwide towards shifting the switching to the optical domain. And the reason for doing this is to save costs, to make it, to make the switches bitrate independent, because by using optical switches, so you can simply upgrade the speed by upgrading the optics at the client side. You don't have to change, you don't have to replace your switch, you just replace your transmitter and receiver. Using these new concepts, these new network concepts, it's possible to implement more advanced and scalable architectures. So the question is, so if we depart from the traditional active optical cable concept and let's try to be more open-minded and see these new architectures, can we get any more benefits from multiplexing? The first observation is that if we have this optical ring, we probably have longer propagation distances in the ring, which means that single mode is probably a good choice. The longer reach makes WDM more attractive, as already discussed. And there is no actual reason why multi-core fibers or multi-level signals cannot be applicable in such a scenario. Now, on second thoughts, it could be possible to apply multi-level modulation and in an elastic networking way, an elastic networking point of view. So, given that we are departing from the active optical cable concept, where the length of the link is fixed, this means we have different propagation distances between the switches, the end hosts. So, as an example, it could be possible to adjust the modulation format depending on the distance. So, if we want to go to the neighboring station, we could have enough loss budget in order to go with PAM4 or even a more complex format like PAM8 and take advantage of the increased throughput that this will give us. If we want to go farther away, then we should probably switch to on-off keying because of the dispersion and the additional losses that are introduced. So this is an example of how this multiplexing can be dynamically used in such a forward-looking scenario. Again, second thoughts on WDM. It could be possible to use a super channel concept. This is widely used in the field of telecom networks. So you pack together the wavelengths depending on their destination. So all these wavelengths are destined to switch one, for example. So you pack them together and you route them all together. So you don't have to process them and route them individually. This actually has been validated a few years ago at the University of Columbia with the concept of parallel wavelength packets. That was not exactly the same concept, but it actually proved the feasibility of this concept. And finally, what about multicore SDM? We could, in principle, also apply a similar concept for spatial superchannels. So, in this scenario, we could route all the cores of a multicore fiber to the same destination. So, for example, we would say that all these 4 multicore fibers, all the data inside them, are routed to switch 1. All the data from these 2 multicore fibers are routed to switch 2, and so on and so forth. This is a concept that has been proposed in the context of telecommunications and could be also applied to datacom, to more advanced datacom architectures. So, as a conclusion, I think it's clear that multiplexing is a one-way street towards scaling optical interconnects. The main multiplexing schemes that we have discussed and analyzed, and people are actually working actively on, are multi-level modulation, WDM, and multi-core fiber multiplexing. Each of them has their pros and cons, and it's actually the interdependence with the available technology and the application requirements that define what's better, what's the best solution for each problem. And finally, the new multiplexing schemes and enabling technologies can potentially open some exciting new vistas in the field, in the frame of forward-looking network architectures. And some, let's say, more specific conclusions regarding the defining attributes for future products or technologies or concepts or what have you. The main defining attributes for future active optical cables for future interconnects is, first of all, the cost, the power consumption, the I/O density out of the box, the data density per PCB area, cable management concerns, heat management concerns, and of course a set of standardized reliability metrics and qualification criteria that are introduced by the industry. So at this point, I'd like to conclude my talk. Thank you very much.
Thank you for the very... Yes. Thank you very much for your very informative talk. So we have time for questions. Please.
What is the typical pitch between the cores of the multi-core IC?
Yeah, it actually depends on the manufacturer. I think it was shown in one of the slides. It's if I try to recall from the back of my head, I think it's about 40 to 50 microns. I think it was even less. These are some examples taken from the literature. This is 40 microns. I think it can even get smaller. It depends also on the number of cores. So in this case, the 9-core fiber, the distance is 23 microns.
So there's no crosstalk between the cores that increase the length of the...
No, it is possible actually to reduce the crosstalk by engineering the characteristics of each of the cores, of the neighboring cores actually. And this is why these cores are shown with different colors here. So in order to reduce the coupling, you can shift a bit the design for the neighboring cores. And actually the results prove that, the system tests prove that you can actually have quite good performance in terms of crosstalk between the cores.
May I ask whether you have noticed that in multi-core fiber, the polarization is affected in a differential way between the different cores. So once you want, for example, to launch only the polarization in all different cores, is there any possibility that they get affected in a differential way during propagation?
If the question is if I have tried it in the lab, no. I would assume that due to fabrication errors, I would assume that there would be some random polarization shifts, but I haven't tested it and I haven't seen it published somewhere, so it's just an estimation. Yes, please.
May I ask you two questions about the size split in the switch?
The size?
Your schematic on slice split in switch.
56.
56. Question one is, I don't know how the feed-forward equalizer works in this schematic.
So yes, you are absolutely right. I didn't describe how this schematic, how everything is put together in this schematic to save time. But you are right that I should give some more details. So this gray board is the optical SOI board, and below this there is a silicon interposer. The interposer is used so that the VCSEL driver and the TIA array are attached to the interposer, and the interposer routes the electrical signals towards the towards the front end of the silicon photonics board through TSVs, through silicon vias. So there are vertical electrical connections that are used in order to route the signal from the VCSEL driver that is below the chip to the electronic components here, like the VCSEL array and the photodiode array.
And each photodiode related to each vessel, right?
Right, yes, this is correct.
And the second question is what kind of covering you do for the MCF using your silicon spot size converter?
Yes, this is actually shown. You will have the opportunity to see much more results for the coupling on this tomorrow on the poster session. But I will just summarize. It is more or less what I described in a previous slide. So actually, this. Okay, let me go back so as not to waste time. So the multicore fiber is attached to a 3D glass waveguide fan-out. This fan-out, it's actually not in scale here. The size of this fan-out is a bit thicker than the multicore fiber, and it starts with a circular arrangement of the cores. It is fabricated by laser inscribing the cores in this piece of glass here. So you can write the waveguides with a circular arrangement that, let's say, is exactly the same as the cores here of the multicore fiber. It's exactly the same arrangement here. And on the other side of this glass fan-out, you have a linear arrangement of the waveguides. So it starts with a circular arrangement and ends up with a fan-out, with a linear arrangement, and also does some tapering. Now, an additional stage of tapering is done through this in-plane coupler, and this in-plane coupler is based on an inverse taper and then an SQ8 overcladding. Yes, please.
So if you have a WDM VCSEL array, if you change the ambient temperature, the VCSEL emission can reach several nanometers. Is this a problem when you do multiplexing and demultiplexing? Do you need to have temperature control on all these parts?
You're absolutely right. Actually, the temperature dependence of a typical VCSEL is about 0.1 degrees. It's 0.1 nanometers per degree centigrade, which means that if you assume, let's say, an operating range of 50 degrees, then that would correspond to about 5 nanometers. So one potential solution is to use a larger wavelength spacing so that you have broad filters. The other solution is, as you mentioned, to use temperature controlled VCSELs, but this is not always the best option in terms of power consumption. And the other approach is to use tunable filters that follow the drifts of the VCSELs. And this actually proves, I mean, if you put down the numbers, this actually proves to be more optimized in terms of power consumption compared to the VCSEL stabilization. Any other questions?
No? Okay, then we can thank the speaker again. And we're moving on to the final talk of today's session from Fabrice Raineri from CNRS. He will talk to us about laser switches and memories using 3.5 on SOI.
Okay. Hello, everyone. So let me first thank Nikos and Dimitris for inviting me to participate to this summer school. And so before starting, I would like to say to you that if you don't understand something, do not hesitate to interrupt me. Or if you want more details on anything, also you can ask. If I can't answer, I'm sure that somebody in the audience can do it at my place. So to start, also I would like to introduce me. So I'm Fabrice. I'm working in France, near Paris. I am an associate professor at Université Paris Diderot, which is in the city center of Paris. And I run my research in a CNRS lab in Marcoussis, which is 30 kilometers south to Paris, which is a laboratory for photonics and nanostructures. And my background actually is more nanophotonics and nonlinear optics, so I come from fundamental physics. But lately, since a few years, we work on this possibility to heterogeneously integrate 3-5 nanophotonic structures onto a silicon on-insulator waveguides to propose some solution, some disruptive solution to make lasers, switches, and also memories. So in this talk, I will first talk about the motivation, but so most of it were already said by many speakers already. Then I will talk about some state-of-the-art in the domain on lasers, optical switches, and memories. So the motivation, of course, you all heard it, and you are participating to an optical interconnect summer school. So the motivation for using 3.5 on SOI, obviously, is to make real these optical interconnections that can be between boards, between chips, and also on chips between like a group of semiconductor transistors. So this guy, Professor Miller in Stanford, almost every year published a new article on the requirements of on this optical interconnects. And of course, he said that photonics can help to overcome the limits of electronics in terms of speed, power consumption for inter or intra-chip communication. But obviously, you face a lot of challenges to make this real. And the first challenge, obviously, is to deliver the functionality that are necessary to achieve these optical interconnects. So you have passive functionalities that are simply like low-loss waveguides, filters, and you need also active devices such as sources, switches, detectors, modulators, memories, etc. And if you want, for example, to go for the small-scale optical interconnect, which is maybe the more far-reaching task, this has to be performed in a very stringent requirement in terms of low power consumption, meaning that you have to be able to activate these elements with the femtojoule energies, which is the same kind of energies that are spent for microelectronic transistors, actually, right now. And also, these single component, they have to be very fast, they perform in an ultra-fast manner, at least 10 giga or more, 20, 40, etc., etc. And obviously, if you want to make on-chip optical interconnects, they have to be very small, and to make them in a very high density. So it has to be, for example, you need like 10 to the 4 to 10 to the 5 devices per millimeter square. So it's a huge number. So meaning that the footprint of each individual element has to be smaller than 100 micrometers square. Then the last thing also is that, well, if you want to converge microelectronics and photonics, it has to be compatible with the silicon, of course, and has to have this, propose this CMOS compatibility for chip manufacturing. So what is how can you go about this? One possible scheme that has been proposed now some time ago by Ghent, for example. This is the scheme. You have the silicon transistor layer, then you have the old small-scale electrical interconnects between the transistors, and on the last level of interconnects, you could replace them by an optical interconnects. And so we believe all here, I hope, that photonics can bring this revolution that it has brought to telecom for ultra-long haul propagation down to millimeter scale propagation distance on a chip. So why 3.5 on SOI? So I like to cite CERTH, which was the inventor of DFB lasers. He said that he was kind of religious, I guess, because he said that God created silicon for electronics, gallium arsenide for optoelectronics, and carbon for life. So what could be the best for the optical interconnect? Dimitris has already talked about it, is that we have two complementary technologies right now, which are on one hand silicon photonics, which have proved, of course, is compatible with microelectronics. Obviously, it can be produced massively in the CMOS fab that are available. And also, it's also good for photonics actually, because of this SOI structure, which is a silicon layer on top of silica, like this buffer layer of silica, and then silicon again. And this silica with silicon has a very high index contrast, so you can make very tiny waveguides. And when it's a ridge waveguide, you can bend it with a radius of curvature as small as 5 microns, so you can make very dense optical circuitry using this SOI. So to me, the advantage of SOI for photonics is really this compatibility with this oxide, which enables high index contrast with the core of the waveguide. So there's been a lot of demonstration of very nice devices using SOI for passive devices. You have WDM filters, you have nice low-loss waveguides, you have add-drop filters, and also you have, even though I don't mention here, so I say it's ideal for passive devices, but you can make also nice modulators with the SOI by implanting it, and as you will be shown, I guess, later in the summer school. On the other hand, you have these alloys, these compound semiconductors, the 3.5, so gallium arsenide, indium phosphide, gallium nitride, etc., etc. So they are these materials were developed for optoelectronics and basically making lasers. Why? It's because by engineering the composition and the structuration of this material, you can get sources, like a source of light and gain from the UV to the far infrared with the quantum cascade laser, for example. It has an extremely high quantum efficiency, and also you can engineer this material not only for sources but also to get a very high nonlinearity compared to other material, for example. So here I represented a typical quantum confined structure that I used for making laser, like quantum dots, just this little island here. These are indium arsenide quantum dots in gallium arsenide here. So this is only like 2 nanometers. And you have quantum wires also. So in the following, I will talk more about indium phosphide-based material. So why indium phosphide? Because it is a natural material where you can use quantum wells to make sources around the frequency that are the wavelengths that are interesting for silicon photonics, meaning 1.3 micron or 155 micron. So you can have very nice quantum wells. Actually, you can have also sources using gallium arsenide at 1.3 with the quantum dots that are made, for example, in Tokyo University. So if you are able to combine these two materials, well, you can provide a lot of functionalities. So what you can do, it's what the previous speaker shown, is that you can also just take a laser in a 3.5 and you flip chip it on the silicon on insulator waveguide circuitry. This is already really nice, but if you think about making thousands of devices on the same chip, you cannot think about bonding even VCSEL arrays one by one onto this circuitry. So it is important to find a way to make these 3.5 devices in parallel, all at the same time inside on the silicon chip. So speaking about technology, so the best way would be to have a way to grow directly 3.5 semiconductor on silicon. Unfortunately, so this is very, very difficult. A lot of people break their neck on this for a long time. And why it is so difficult is because the lattice constants of these materials, they are very different, up to 10% of difference in lattice mismatch. And also you have very different thermal expansion coefficients. So why thermal expansion coefficients mismatch is an issue is because usually when you grow your semiconductor, you go to high temperature, like 600 degrees. And then when the temperature change, the lattice don't move at the same, in the same manner, so then it breaks the material. So there are lots of research in progress to overcome this problem. And basically, there are two ways to overcome this problem. One way is instead of growing bulk material on silicon, you grow a nanostructure, and like this, you release the constraint of lattice constant mismatch. This is what people do, for example, here it's in Berkeley, here it's in IMEC, where they find some way to grow these nanostructures on the silicon substrate. So this is not easy. It's right now it's very, very popular research because it can provide a nice solution to integrate devices on silicon like this. Another way is use metamorphic or seed layers on silicon. It's a bit more complicated. It's not more complicated. It's another way to do it. Basically, what you do is you open a via inside the silica layer on top of silicon, and then you grow your 3.5 in these vias. This material is bad. It grows badly inside the hole, but then when it reaches on top of the hole, you change the methods of growth and you make lateral growth. And the material between two holes is quite nice, and you can make nice active layers to make some devices. These are other drawbacks linked to the fact that you need to have thick layers, and it doesn't allow you everything in terms of design. So all in all, right now, there's still no results comparable using this method to grown to a 3.5 semiconductor directly grown on 3.5. So right now, it's still a very challenging research. The other way to do it is to make wafer bonding. What is wafer bonding? Well, basically, what you do, you take your silicon chip, your 3.5 wafer, and then you find a way to stick it to stick one onto the other. So there are different ways to do this. You have adhesive bonding, where you can use like a polymer, which is can be cured and act as a glue between the two wafer. You can have you can prepare your surface in a certain way to activate some dangling bonds with this oxide, and to make some nice molecular wafer bonding. This is what Leti does, for example. And you can make wafer fusions by putting at high temperature the two wafers, and sometimes it works. So basically, here is an example of the technology we do at LPN. We use the same technology that was developed at Ghent University in Belgium, which is the adhesive bonding. And basically what you do, you spin coat the resist, the polymer onto your silicon chip. You put a very thin layer, like a couple of 100 nanometers, and then you stick your wafer by pressing and putting it in a high vacuum chamber. When it's heated up, it cures and it becomes like glass. And then you have to remove chemically your wafer. Or what you could do if you want, if you think for future application, you can make smart cuts of the wafer like they do for SOI wafers to be able to reuse your 3.5 substrate and bond another layer on top of silicon. So presently, this is what I'm going to talk about in the future part of my talk. It is the best solution of all for 3.5 on SOI. So one of the most important components that has to be achieved for the optical interconnections is, of course, the lasers. And there are two clear-cut goals there for research in lasers. I would say that there are some people around that work on sources that would be able to replace telecom or datacom sources. Like the goal here is to have almost the same sources that you get using 3.5, directly 3.5, like 1.3 or 1.5 micron, power of tens of milliwatts. And their goal is to make this laser in a cheaper manner, actually. So this is one of the goals. The other goal is to go for on-chip interconnection, and here you have to make what's called micro lasers. And here, so the output power is about 10 to 100 microwatt. The requirement, the footprint is very small, and it has to be power efficient. So here I'm going to talk about 3 different paths that were undertaken during the last years. So the first path is the one that has been pioneered by people at University of Santa Barbara and Intel. It's maybe it's a starting point in the domain, I would say. And what they did is they bond directly the 3.5 wafer on top of SOI waveguide. And what happened here, so they have, you can consider that the two materials are in contact. There's no oxide layer between the two. And what happened is that if you calculate the optical mode here, it is a mode, one more. It is a mode that is confined at the same time between inside the silicon and the 3.5. So by playing on the geometrical parameters of your structure, you can change the overlap of the field with the active material, for example, which is at the interface. Okay, it's here. Here, for example, you have the active material. So by playing on the width, for example, of the silicon, you can push the field towards indium phosphide and get more gain. This hybrid mode is something that you can engineer, but the problem is that even by making the best you can get like a few % of overlap between your quantum well and the mode. So this is a problem for efficiency. So the first demonstration that they did in 2006 was simply a Fabry-Perot edge emitter laser, where they cleave the chip at each edge, and they get a nice laser emission with some milliwatts out and working at fairly, 40 degrees temperature. So this was their first demonstration. So then the story for them didn't stop at all. Actually, they are really leading team group in the world on this domain. So they were able to make a mode-lock laser to emit a pulsed, to have pulsed emission here by playing on the contacts of these two parts of the laser here. They made a DFB laser to have single mode, nice single mode emission by integrating inside the SOI grating here. It's here like this. And they made also racetrack lasers and actually a full with integrated with detectors too. So they made a very impressive devices like emitting at several wavelengths, like lots of things. So the other approach that I would like to mention is the one that has been developed in 3.5 Lab, Université Paris Sud and Leti and Ghent. It's another way to engineer your structure to get some light inside the silicon. So I forgot to talk about it, but obviously the idea is to have the laser emission and to have the maximum power inside the waveguide, the silicon waveguide circuitry. So these two materials, you have to know that the refractive indices is almost the same, so it's good for optical compatibility. But usually the thicknesses that are used to make the lasers and the SOI waveguides are very different, so that the effective index of the two modes propagating in the two materials are very different. So it is not something a trivial task to couple light from the 3.5 to the silicon. 3.5 has a typical thickness of several microns, and SOI only 350 or 220 nanometers. So here it is represented here. So what these guys did, they engineered a tapered zone. So here the two layers are separated by a low index layer, which is a BCB. It's 1.5 as the refractive index, and you have evanescent wave coupling between these two. So how evanescent wave coupling works? To have good efficiency, you need to have the two for the two levels, the two parts, the same effective index. So to achieve this and to have it nicely, they implement tapers both in the 3.5 and the SOI levels to achieve perfect transfer, almost perfect. It's very close to 100% transfer of light inside the silicon level. So basically, what you do is that in the 3.5 layer you have a higher effective index. You reduce its size to decrease the effective index of the mode, and in the silicon you do it in the reverse way to match it. So they had very nice results with also milliwatts inside the emission, in milliwatts emission, with also like emission until up to 70 degrees temperature. Now about the micro nano lasers. So actually there are, I would say, only very few teams that work on this, because to me maybe it's the hardest way to achieve, to go for this type of these lasers. So the first possibility, that the first thing that was investigated is to make a micro disc laser on top of a SOI structure. So here the structures consist of a microdisc, which is coupled through evanescent wave coupling inside this SOI waveguide. So in the microdisc, you know that there are modes, whispering gallery modes, that are traveling around the disk, and this mode can exhibit laser emission when there's gain. And so these lasers, they are nice because they have footprint that are quite reduced. It's only 100 micrometer footprint. You have a picture here of an optical image of this type of lasers. And at the time, these guys demonstrated nice laser emission with tens of microwatts in the silicon waveguides, and with a fairly low threshold of about half a milliamp. So this was already nice. So how can you beat this? Actually, one way is to use nanophotonics. And so I don't know your background, but so the nanophotonics, there's one emblematic structure, which are photonic crystals. I don't know if you heard about them all. So basically, it is the photonic analog to atomic lattices. And basically, in this structure, the dielectric constants plays the role of the atomic potential in atomic lattices. And you can really get almost an extensive control of light propagation by playing on the optogeometrical parameters of these photonic crystals, such as size of the holes, lattice constant. You can tune this lattice constant along your photonic crystal to get a very nice cavity. And right now, these cavities, the photonic crystal cavities, are the cavities that exhibit the highest Q over V ratio, meaning that it is the cavity for an input power. You get the highest intracavity intensity. So this is very good for light-matter interaction. And then when it comes to laser, of course, if you get a very high light-matter interaction, you get very low threshold. So this is what we worked on at LPN. And basically, we worked with this photonic crystal structure, which it's called nanobeam structure. It's just a rich waveguide made in a thin indium phosphide membrane, like 250 nanometer thick indium phosphide membrane. You drill holes inside of them. The size of the hole typically it's a 200 nanometer diameter, and the lattice constant is about 350 nanometers. And by engineering the structure, you can get very high Q cavities and make a laser when you incorporate quantum wells inside the epi layer. So these structures were bonded, were made onto SOI. So here you have the nanobeam cavity, and this is in transparent here the SOI wire below. And these two, they are coupled through evanescent wave coupling. And we demonstrated that it's possible to couple more than 90% of the light from this cavity, the emission to the waveguide. So here it is just an infrared image of the emission. We pump them optically right now by the surface here. So here this is the emission by the surface. So here you have the propagation of the light inside the silicon wire. This is about 4 millimeter long, and then you see the light outputting the grating couplers etched at the end of the SOI wires. So we have a nice laser emission as proved by this light curve in the log-log scale. And what is nice from this laser, so they have a fairly low threshold. Here it's about 10 microwatts of optical power, so meaning that if you're able to contact them electrically, you get a 10 microamp approximately laser threshold. Okay, so what they are very nice, why are they are very nice also is because they are very small. They have the potential to be directly modulated at a very high rate. This is also an important aspect of these lasers. Okay. So now I'd like to continue with the switches. And actually, I'm going to talk about optical switches, meaning that what I'm going to talk about is I have a system which is able to control the propagation of light by light. I won't talk about electro-optical switches or modulators. You will have some talks about it later during this week to explain you the concept of electro-optical modulation. So here I want to change a bit from what maybe you're used to all optical switching. So one way to do it is to have a cavity, okay, which is coupled to a waveguide. It's side-coupled, and what you observe in transmission, you observe a dip in the transmission at the resonant wavelength. Here, for example, 155 micron. So if you are able to change somehow the refractive index of this, the constituting material of your cavity, what you will observe is a shift of the resonant wavelengths when the pump is on. And then if you set a signal at this in a resonance in the beginning, in the first step here, when you shift your resonance, then now your signal can pass through your system. So this is a kind of a switch. So in all optical switching, you have several processes that can provoke this change of refractive index. So the one of the process is, okay, you have some light pump that is absorbed by your system and by your material, and when it's absorbed, it excites some carriers inside the material, and because you change the concentration of carriers, you change the refractive index, and usually you observe a blue shift of the resonance. That's what I represented here. You have other processes like thermal effects, for example. If you have a lot of absorption, you get somehow also heating due to relaxation of carriers, intraband relaxation of carriers due to phonon emission. Then this redshifts your resonance. So when you are able to promote the refractive index due to the creation of carriers, either by direct absorption or two-photon absorptions, for example, the dynamics of this switch will be determined completely by the carrier lifetime, meaning that if you want to recover your system, you have to wait that the carriers that you created recombine to go back to your initial stage of your system. So usually, this carrier lifetime in semiconductors, so in silicon, for example, it's nanosecond, usually. In 3.5, it's also a nanosecond, but when you drill holes, also in silicon it happens, when you drill holes basically inside your material, you have surface recombination on the edge of your holes, and this increases the speed of carrier relaxation. So you can get a couple of hundred of picosecond as dynamics for this switch. So this is not so good actually, because we want to have a much faster switches up to much faster than 10 gigahertz, for example. And so what can be done, for example, with the microdisc? This was done also at Ghent University. So the system is this one. So you have your microdisc. It is you have several wavelengths. You have several resonant wavelengths because the disc has here its size is about I don't remember. I think it's 10 micron or something like this. And you have the free spectral range between these two, which is about here 25 nanometers. So what you will do, you will inject your signal that you want to change in this wavelength, and you will pump the system into another resonance. You do this to decrease the power you need to provoke an efficient change of refractive index. So here, so they did this. So they see somehow a conversion of the signal at this wavelength. You modulate, this one is CW, this one is modulated, okay? And once this one arrives, it perturbs the system, it shifts the resonance, and you see an increase of the signal at the output, like here, okay? This is, they launch pulses. So this is the pump. This is the response of your signal. So here, so as I told you, if you don't do something special, this recombines in 200 or a couple of hundred picoseconds, so it's not so good. So to increase the speed, what you can do is to reverse bias your system to sweep out the carrier from your structure. And this is what they did here with this type of bias, and they observed like a recovery time of about 50 picoseconds with the switching energies of about 400 femtojoule. So this was a nice result. So now what we did at LPN and how we wanted to improve this performance, actually we played on the surface recombination of carriers. And so instead of applying voltage, what we did is that we put some quantum wells at the very surface of the structure, so that when carriers are created in your structure, they are captured by your quantum wells. And because you are at the very surface, you have plenty of centers of recombination for your carriers, and this accelerates drastically the carrier recombination. So the structure is this one. It's the same kind of structure that we use for the laser emission. And so here, for example, to demonstrate the capability of the switching capability of our system, first of all, we at LPN we perform what is called a pump probe experiment. Basically, you have pulse sources, like femtosecond pulse sources, and what you do is you probe your system with this short pulse, so you can probe this spectrum, okay, like this, or you probe the output power. And with the pump, what you do, you perturb your system, and what you look at is how the probe is perturbed by the pump as a function of the delay between the two. So we perform a degenerate pump probe experiment, and well, this is a kind of complicated detection system. We use it's called a balanced heterodyne detection, and this basically allowed us to measure the change of the output of the probe as a function of the delay, and we saw that the system recovers with a typical time of 12 picoseconds. So it's a very, very fast recovery time with switching energies only of a few tens of femtojoules. So this is a very good result. And next, the next step was to assess this result in a system experiment. And actually, it was the first time that some system experiments were performed on photonic crystal switching cavities. And this was done in another CNRS lab in Brittany. And what they did is they performed the wavelength conversion experiment that I showed you with the microdisc. So here they probe inside this resonance, and they pump with the 10 gigabit per second signal. And what they observe is the following. So this curve represents the bit error rate as a function of the power received onto your detector, and so this is the reference bit error rate here with this nice eye diagram, and this is the output we have from our cavity. So here the bit error rate is degraded by 4 dB, but these 4 dB they are only linked to the relatively low contrast between the on and the off state. So it's because this resonance is not so deep. But basically the shape of these two, they are the same. So it means that the system is not limited by the speed of the cavity, the nonlinear cavity, but only by the contrast in the resonance. So here the peak power was about some milliwatts, and it was a error-free wavelength conversion. So actually, we performed also 20 gigabit, and it works also fine. Another application of this cavity switching is, I think it's a nice example. It's a noise limiter. For example, you have a signal where you have a lot of noise onto your ones in your data. Well, because you have a nonlinear response of the transmission as a function of the power, you can limit the output signal to a single value here, and you can reduce drastically the noise of your signal, for example, by 12 dB. So it's a nice application of this type of devices too. Okay, yes, so we performed also actually all optical gating, meaning that we can route the signal from one waveguide to the other by using another type of design of switches. Basically, you have your cavity. This cavity is coupled to another indium phosphide waveguide. Here, it's a mirror to prevent the light from going this way. And then the light goes this way, and it's coupled to this waveguide. And we have close to 40% drop efficiency, which is close to the 50% limit in this system. Okay. So the next device I wanted to talk about is a memory. So Dimitris talked about memories too, and they can be maybe it's even a more farther-reaching goal to implement optical memories together with CMOS, but still it has been always a challenge to make a memory with photons because of their intrinsic nature. You cannot fix them in some place, and then so it's not something so easy. So how do you make a memory? What you use is a bistable system, basically. I talk about random access memory, of course. So this memory, they are based on a bistable system. What is a bistable system? It means that for the single input power, you have two possible output powers. So, and you can switch between these two optical powers. For example, here, if you have this input power, you have these two states. What I can do to switch to the upper state, I launch an optical pulse, which takes my system to here, and when it comes back, it stays here. So this is the way you perform your logic operation. So this bistable system, they have important applications such as data processing, logic functions, transistors, memories. And how do you go about them with the optics? So usually what you can do is you take a resonator, which is filled with a nonlinear material, meaning that you can change the refractive index basically as a function of the intracavity intensity or the input power. And you have two types of nonlinearity that are usually used. One, so you change the refractive index, or the other one, you can change the gain or the absorption. So these are the two ways to achieve optical bistability with the resonators. So here I'm going to talk about only what happens with the gain medium. And the first thing I'm going to show you is again work from Ghent about bistable operation of these microdisc lasers. And what happens in microdisc lasers? So when you drive them, basically you have two possible modes. One which is rotating in the clockwise, and the other one which oscillate counterclockwise. So in principle, because they are traveling waves, you shouldn't have a competition between these two modes. But as you increase the power, of course, you can have a competition through gain or defect inside your structure. And then at some point, you have only one direction emission. And by sending a pulse in the other direction, you can flip the direction of emission to the other one. So this is here what is represented. So here you have at low bias current, you have bidirectional operation, and once you increase here, you have unidirectional and bistable operation. So how does it work? So for example, if you start from a laser which is driven in the bistable range, it emits inside this clockwise mode, and the light is coupled to the silicon wire in this direction. To switch the direction of emission, you launch an optical pulse, and then what happens in the laser is that actually you will favor the other direction of emission through this pulse, through the competition. So then it's like this, and then you go to the C level. So if you're looking at the output on the left here, so you have something at the beginning, then when you launch your pulse, crack, you have nothing, it's all in the other direction. And to come back, you launch a pulse in the other direction, and then you get the bistable system, the switching operation between these two. So this operation, this result was very nice, and because of the nature of these bistable systems, the switching energies that you can use to flip the memory are quite low. It's about a few femtojoule, and the switching speed, what is pretended in the article, is about 60 picosecond. But this it's not completely assessed in this paper. Okay. Now, what about photonic crystal lasers? So the way that we performed our bistable operation is a bit different than in microdisk. It is based on injection locking of the laser. So how does it work? So basically, imagine this is the spectrum of your system. So you have the laser emission at this wavelength, and what you do, you inject light inside the silicon waveguide just on the red side of this laser. What happens is when you increase this power of the injection, you change the carrier density of inside your laser, because you have a stimulated emission that is stimulated by this injection. Basically, as you increase the power, you get more stimulated emission at this wavelength, so you deplete, you change the carrier population, and at some point, what happens is that the carrier density is such that the system locks inside the injection. So it lasers exactly here. So you get no emission anymore here. So what happens now is that actually the wavelength, the resonant wavelength of the system, which was here in the beginning, this wavelength is now on the injection. It means that to come back to the same intracavity incident injected power, you need to decrease the input power to a lower level, because now it's resonant. Okay? So here it's not resonant, so the injection is quite poor, okay, of this laser. And as it is resonant, of course, the injection is very efficient, so you have more intracavity power for the same input power, okay? This is how it works. So to come back, you need to reduce more the input power to come back to the first state, as it is shown here, to recover the unlock regime. You can do this, or the other way you can do, what you can do is to increase the carrier density with the pump, for example. It's the other way. So now, in the following experiment, what I'm going to show you, it is the signal which is filtered around this lambda unlock here in the beginning. And if you look at what happens as a function of the injection power, you will be able to observe an hysteresis cycle. So this is the experiment. So here, this is our device, and what we did, we have this CW source as an injected light here, the CW injection, and then to flip the system from one state to the other state, we have an optical pulse provided by either femtosecond or picosecond source here, and you monitor the laser, the emission at lambda unlock as a function of the power of this tunable laser. So, for example, the signal that we monitor is the following. So here it is the CW input power, and at some time we go to 0, we reset. Okay. So by launching an optical pulse, here, so this is the laser emission at lambda unlock. So when it's unlocked, this signal is high. Okay. And when you launch this pulse, this signal becomes low and it's locked, and it stays, as you can see, like seconds. So it's a very stable system, and you have a nice memory like this. So to recover your system here, we unlock it by diminishing the input power. So now if you make this experiment as a function of the injected power, this is the hysteresis cycle that you get for this system. And so what you can see is that the injected power necessary to be in the bistable range they are quite small. They are of about a few microwatts. And what is noticeable is that the switching power is only here, like less than 20 microwatts, so it's a very low power. The switching energy actually is around 0.1 femtojoule. It's a very low switching power. And the memory, so it stays, here it's measured for 2 seconds, but it can stay even more, actually. And what I really recently measured is that the speed of this memory is faster than 40 picoseconds, I would say. It's like, actually the recovery time of what is limiting this system is basically the recovery time of your laser, and what we saw, it is only limited by the photon lifetime inside the cavity, which is about 20 picoseconds for this type of cavities. Okay, so to end actually this talk, I would like to come back to my first one of my first slides, which is about this conversion of microelectronics and photonics, and what I would like to end my talk by asking you: do you think that what is the effort that has to be done to achieve all these challenges? Maybe in the rest of the summer school you'll get more insight about this. So with this, I end my talk, and I thank you for your attention.
Richard.
Yes.
Would you mind going back to the slide where you showed you flipping the direction on the microdisc laser?
Yeah.
Yes. I was wondering if you could explain properly the mechanism by which the pulse in one direction stimulates the laser.
Okay. So if I remember well, it's exactly this. You stimulate the emission inside the other direction, so that it means that actually what you make, you deplete also the carrier concentration inside your laser, and to decide which way it has to go. I mean, the stimulated emission starts with your pulse actually. So then when it's locked onto this side, it should go on the other side. I don't know, maybe Bert can tell more about this.
You invert, so you have lasing counterclockwise. You invert the pulse in clockwise. And because you invert this pulse, you have the mode to increase the power in clockwise traveling mode. And then through cascade suppression, more and more power goes into this clockwise traveling mode, eating away the power of the counterclockwise. And as soon as the power in the clockwise mode is larger than in the counterclockwise,
It starts.
Self-amplifying, and you switch completely over to the other one, from one state to the other state.
So the injection pulse is larger than the already lasing.
Yes.
Yes.
Any other questions?
So you actually mentioned that you can change the refractive index in order to change the intensity or to switch the light.
Yes.
Can you do the same with the phase of the light? I mean, can you switch the phase between 5 or 0 or something like that?
So yes, you can do. You can do it, but basically to do it, you shouldn't use a cavity. You can use a waveguide that you, by changing the refractive index along this waveguide, you can change.
This is a well-known technique, but
Yes.
Can you apply the same technique that you applied here for changing the phase?
For all optical.
For example,
a good question. I don't know. I don't know. Maybe but the phase should change because you change the wavelengths. But
I mean, can you make the hysteresis like you showed for the phase?
I'm not sure because actually we performed also some experiment using the switches here. You also to regenerate the phase of this type of. If you degrade the phase of the input signal, you can recover also. You can regenerate also the signal in phase. So I'm not sure it doesn't change the phase actually. I don't think so.
Okay,
Insane. Yes. Okay.
I have one question. It's kind of an old-fashioned question, but have you seen what is the polarization dependence of your optical switches?
Well, here everything is in the SOI, so it's a T. It's T polarized.
So what happens if you know?
Yeah, if you change the polarization. Yeah,
Yeah,
basically here, if we have quantum wells, usually they absorb only when for T polarization, meaning the electric field parallel to the plane of the quantum well. So usually, if you polarize in the other direction, you have no absorption of your light. So it should decrease. So for the pump, it will decrease the nonlinear interaction. But if you go, people do this kind of experiments actually to measure the dynamics also of SOAs. For example, they probe the SOAs in TM and they pump it in the TE, so that then they induce also a nonlinear effect on the TM side to separate the two signals.
Okay. Any other questions? No? Okay, then I guess we can thank the speaker again.
Thank you.
And with this talk, I guess we're closing today's session. Let me remind you that our next session is tomorrow at 9 o'clock in the morning. It's about the industrial perspective. We're going to hear talks about speakers from the industry on the requirements for optical interconnects. Let me also remind you that tonight you can join us for a few drinks if you're up to it, to Omilos Bar later on at 9 o'clock. So if you're in the mood, just feel free to join us. And if you need any more information, you can come to me or Nikos or Stella. Okay, so thank you very much. See you tomorrow.